be live streaming it as well,
Yes,
right?
Yes,
we are.
Oh, we are.
it's live now.
Good. Think of anything else?
Anything else, David? I think Zach's excited to start talking to us about his talk.
About 10 minutes?
Okay.
All right, cool.
So always come to us, you guys, if you have any questions. Let us know.
Music is awesome.
Jamie had music. Alex did the music last time, didn't you?
No, I didn't, because everyone else would be crying by now.
Nothing but ballads?
He's in a band.
Alex, why don't you come up here and explain the study and everything that you're gonna do? Do you wanna do that and talk to them all now?
No pressure, no.
Yeah, go ahead, Alex.
Why don't you just sit here and do that from here?
Yeah, you do it from there, you can do it from right there, just tell everybody about it
Right.
and what you do.
Okay, well, we don't have to do that.
Yeah.
So people can see.
I'm gonna, let's do that.
Okay, so I can see that.
Yeah.
Hello. Hi.
Tell where you live.
Yes, well, so I used to live in Pittsburgh until like 6 or 7 months ago, and then I decided to move to Estonia because it's much nicer now. There was just a job opportunity. So what I do is basically I study these types of events, not only like here, but also in other places. And the main thing that we're focusing for this particular one is to look at how does it work when you are sort of coming and leaving. So this is why we have this sign up sheet, right? Just to figure out, okay, what does it do with the teams? And the overall goal for this is to tell organizers afterwards, okay, so you need to do this in order to make it a nicer experience for the participants, or you need to do this in order for them to learn more, right? So basically trying to figure out how does this hackathon thing work? Because when we started like 3 years ago or so, we saw that everyone was doing hackathons, but no one really knew how to do it, and everyone was sort of doing it kind of like, oh yeah, we just gather a bunch of people and then it's going to work by itself, which sometimes it does, but sometimes it doesn't. So that's basically kind of the thing. So I will be sort of around helping you hopefully and looking at what you're doing, and afterwards we're also going to send you a little survey, and maybe I'm going to ask you to do like a short interview, but that's sort of determinable by how it goes. And if you have questions, I'm here. So.
Thank you.
Yeah, but seriously, don't let me decide on the music.
Yeah, go ahead, sorry.
Jamie made a playlist for us.
Yeah, there was a playlist on Spotify.
The students actually made the playlist. So,
We did have music going at some part.
oh yeah,
Yeah.
they made the playlist as they went. It was.
Oh, yeah, as they went.
Yeah.
I remember that it was very hip hop.
Yes, it was.
Just go ahead and jump in.
All right, well, good morning, everybody.
Situation.
Oh, yeah.
Hey, my name is Zach Muir. I'm a solutions architect for our company, OmniBond. And just want to give you guys an introduction onto what you're going to be doing today with what project you're going to be using. So this is Cloudy Cluster. And just since we saw in some of our early, polling from you guys that there was very levels of experience. So anyone that didn't have any previous experience with HPC, I was going to give a quick rundown. So high performance computing typically consists of a login node, a scheduler of some type, shared file systems, and compute nodes. Now, depending on what your workloads are, there's a large amount of hardware available that makes each workflow more efficient. So in traditional HPC, there's varied workflows including MPI jobs, GPU jobs, which now with like tensor cores and things like that, it's not just graphically oriented jobs, it's also machine learning and deep learning, data intensive computing using the Hadoop ecosystem, and interactive computing with Jupyter Notebook, Jupyter Hub, machine learning, and real-time workloads. So HPC in the cloud allows you a lot of freedom, because while you might have access to on-premise resources at whatever institute you're from, you've got to deal with queues, you've got to deal with possibly antiquated hardware. So on the cloud with AWS or GCP, Amazon Web Services, Google Cloud Platform, there's a diverse selection of hardware resources. And the best thing about it is that they're constantly adding the newest, greatest, best hardware that's available on the market. Access to a much larger scale of resources as well, whatever scales to whatever kind of job that you're kind of trying to run. No queue times, aside from the initial spin-up time with Cloudy Cluster, and less or no associated infrastructure costs. So just the runtime, and that's it. So Cloudy Cluster is a self-service cloud-based HPC, and it's designed to mimic traditional HPC environments with the presence of a login node, scheduler, and storage nodes, with the added benefit of total dynamic compute scaling using the CCQ metascheduler. I don't know if any of you are familiar with QSub, but it's basically a metascheduler that works on top of that. So currently, these are the technologies that we leverage with Cloudy Cluster. We use OrangeFS with AWS, we leverage OrangeFS on EBS, S3 and EFS. And we have job-driven elastic compute through CCQ, which the talk after mine will get into a lot more detail with that. We leverage Torque and Slurm schedulers, and a good set of libraries and software to get people started with, trying to do some different simulations, jobs, anything that they might be interested in. Now, in the event that you don't see something on here that you're interested in, we also have a method to customize your image on AWS and GCP. So you can install whatever software you need, and that'll be present on all your images that you're dynamically spinning up. And we'll give you guys that information. So this is the general architecture for AWS. When you submit your HPC job, it'll go into CCQ, and basically your jobs will be spun up through autoscaling groups and sent out by the scheduler to each one of these nodes that's spun up. And also on GCP, we have the same kind of infrastructure with compute engine as well. So this is just a video showing the initial marketplace launch. What you'll do is you'll go to the actual marketplace listing and spin up things from there. So choose a region to launch into. I guess with us being in Texas, doesn't matter too much.
It's cheaper in the US.
It is cheaper in the US. So we'll walk you through this process as well once we get to that point with you guys. But everything should be chosen with the template should already be in there. Yes. So a lot of this is self-explanatory through the demo. But yeah, you'll have to have a key pair on EC2 or GCP. And just for the purposes of this, we use a 0.0.0.0/0 CIDR, an open CIDR. And once things are launched, you'll see a stack being created in CloudFormation, and you'll have an IP to hit once that create is complete, And that will get you access to your initial control node. Okay. So that's your initial control instance running and in your account in your EC2 console. Hit that IP. And your domain will attach to Route 53. And you'll have to enter in that PIM key that you initially spun up the stack with. Put in your credentials for login with a native cloud cluster login that you create on this page. And then you'll get into your initial overview, which will show that you have no current HPC environments. And this is where you'll go to create whatever HPC environment that you're interested in making for whatever job that you're trying to run with the hack. And also, once you're finished using your resources, you'll go to the administration tab and remove your control instance and database. And this will just clean up any resources, since there's a lot of different resources that get spun up in AWS. It'll just make sure that there's no associated further charges on your account. So just as a sample, maybe give you guys some ideas. We made an open foam sample for a fluid dynamics conference that we went to show prospective customers just what they could do with Cloudy Cluster. And we do have VNC enabled, so we're able to get into the instance, into the login node, and use it like a traditional VNC terminal. So what we had here was just an open foam job run. Here's using CCQ sub. So the job was submitted with the mBreak job script, and this is a basic Torque Slurm script that you'll use when you're submitting your MPI job. So this is just statting that job that was made, and just the outputs from that job that created some usable data. And we also did the same thing for weather researching and forecasting model, WRF. Again, from VNC inside of a login node, configuring the run on shared space so that it's across all the images. See that JavaScript. Okay. And again, we do have WebDAV, so that's how we were able to pull out our output from that job, and then do some of the post-processing stuff either locally or wherever you needed to do that. So in this case, we did local post-processing on some weather modeling data. I'm sure that this means a lot more to someone that's in weather researching, but we just got a really cool graphic out of it. All right. If anyone has any questions, we'll move on to Brandon's talk on CCQ.
All right, so hello everybody. My name is Brandon. I'm one of the developers. I'm a software developer here at Omnibon, and so I'm going to be talking to you a little bit more about the CCQ functionality and another product that we've been working on, open source project called CCQ Hub. So Zach briefly talked about CCQ, but CCQ is a meta scheduler for traditional HPC schedulers. So I don't know how familiar everybody is with HPC schedulers, but basically they run as a bash script with certain directives that specify how many compute or how many nodes, how many cores, how much memory, how much you want, and then traditionally the scheduler allocates that to a certain amount of resources that are local. With CCQ in the cloud, the difference is the resources, you have all the resources in the cloud, but you don't need them to run all the time. So CCQ just kind of automates the process of when you submit a job, it actually parses out the information that you specify in your job script and goes and spins up the appropriate resources to run that job in the cloud without you having to figure it out or do anything like that. You just submit the job and it does the rest. So it also handles deletion along with creation. So you submit the job, it runs, the resources come up, the job runs, job finishes, it tears down the resources when you're done. So you pay for the runtime, but you don't have to pay for the cost of the compute instance to keep running. And it also allows you to utilize different instance types. So in Amazon, Amazon or Google, you have plenty of different instance types to choose from. Some of them have lots of memory, some of them have GPUs, some of them are spot instances. So it allows you to spin up different types of instances for different types of workloads that you're not always going to want the same hardware. You may need different hardware for different workloads. So how it works in the most simplistic nature is you have this job script that you submit through CCQ that runs on any of the instances running within Cloudy Cluster. There's a couple commands that I'll talk about later. And so once you submit this job, basically what it does is it runs it, there's a process that runs and it parses the information of what resources you're requesting out of it. And you can do this through a couple ways. You can do it through the standard scheduler commands, or you can do it with specific directives that you tell it, I want this instance type, I want this exact instance type, spin me up 10 of these. That's what I want to use. And so what it does then is once it determines what resources you want, it will actually go create all the resources, launch them, hook them up to the scheduler so that it runs just like it would on a local resource. So researchers who are used to running this locally don't have to change anything. It runs the exact same way through the scheduler. Everything works the same way. The scheduler handles things the same way. The only thing that's different is that the resources are created on demand instead of already existing. And then once those resources have been created, it sends the job to the scheduler, like I mentioned, and the scheduler just launches the job. And then it also is once there's no more work to do, once the job's finished, the instances, they wait until the nearest billing period, which used to be an hour. It's now per second on both clouds. So it just, once the job finishes, it tears everything down and goes back to normal. You submit a job, it spins up more resources. So CCQ is all driven through these job script directives. And this determines what resources to launch that you can specify within the job script. And so we utilize two different types of directives. There's CCQ specific directives that are just specific for CCQ, but then we also use supported HPC scheduler directives. So just the standard ones you'd see with the standard HPC or the HPC schedulers like Slurm and Torque. And these directives also can be used. You can specify multi-cloud arguments in the script. So you can have the same script that runs on Google and AWS, and the same arguments can be in the same, they can be in the same script, and CCQ is smart enough to know which cloud is running on within Cloudy Cluster, so it'll automatically use the right, spin up the correct resources in the right cloud. The other thing is that if you specify both a CCQ directive and an actual scheduler directive, when creating the resources, CCQ will actually, the CCQ directives override the scheduler directives, because you're explicitly stating you want this certain thing. And so the scheduler will still use your directives as normal, but CCQ will spin up whatever resources you've overridden with its commands. So kind of show just a little sample script of what it kind of looks like. So the script on the left is set up to run in multi-cloud. It's just an MPI prime. It's just an application that runs an MPI and finds the prime numbers between 0 and a really big number. And so on the left here, where we have this, you can see the arguments that we use. The #cc is the target, or is the directive that we use. And then this AWS IT specifies an instance type within Amazon Web Services. And then this GCP IT specifies a instance in Google. And this also, we have this TL is a time limit. So you can specify that I want this to run, say you know you only have enough money to run this for an hour. And so I want this to only run for an hour, even if it's finished or not. So you can set a time limit and say at the end of an hour, kill this regardless of what the processing status is. So you can have a long running simulation that you want to let run for a certain amount of time, and then you can set a time limit, and once that time limit's reached, it'll automatically tear everything down without the job having to finish. Or if your job gets stuck in a loop or something like that and just keeps running, then that kind of is a protection against that. So in this script down here, this S batch is a Slurm HPC scheduler directory, and that N is the number of nodes. So this is saying I want 4 nodes. And so we're specifying up here the types of instances that we want, and then it's going to automatically determine that from this directive that you want 4 of these instances, because that, and you can also specify the 4 with the CC argument as well, but the scheduler itself needs to know how many nodes to assign, and so that's what that directive uses. And so then on the right is kind of a simpler job script. The only CCQ argument that we use is the time limit. And then the PBS is the torque scheduler directive. And the nodes, of course, is the number of nodes. And the PPN is how many processors or cores that you want per node. So that's going to spin up 2 nodes that have at least 2 processors. And it's going to spin up the cheapest instance that has 2 processors. So if you don't know necessarily the instance type that you want, but you know you want it to have so many cores or so much RAM, you can specify that and it will find the appropriate instance type. But these 2 jobs do the exact same thing. They just specify different things to the meta scheduler to spin up different types of resources. So some of the features, like I mentioned, the time limited. We also have the concept of placeholder jobs. So you can also just say, if you want to just experiment around for an hour or something, you can actually just spin up instances that you can then log into interactively, like with the GPU, or if you need to do some rendering, or like with VNC. So you can spin up the instances, and then it'll act like they're fixed resources, so they won't delete until that time limit's up. So you can go in and do debugging and checking your runs and all that type of stuff. We also have HPC workload support. So if you want to watch hundreds of thousands of jobs over a short period of time, you can start. We have the submit instantly option, which allows you to, normally when you submit a job, all the resources are supposed to be there. So if you need 4 nodes for an MPI job, you need the 4 nodes before the job can run. With the HPC or the high throughput, all the jobs tend to work independently. And so you don't need to wait for all the resources to come up. You can start running those jobs as the resources come up. So we did a run that we spun up 1.1 million CPUs in AWS, and it was a high throughput workload. And so as more instances were spun up, we added more jobs to the queue to run. So that way, as we got up the instances, we ran the more jobs. We also use spot and preemptible instances, so you can use discounted pricing on AWS and GCP. Both of those are supported. GPU also support, and the auto resource termination, which I previously mentioned. So how you actually use it, it's relatively similar to a traditional HPC scheduler. You've got 3 commands basically. There's the CCQ sub, CCQ stat, and CCQ del. And the sub is for job submission. The Q stat is just for monitoring. And then the Q del is how you delete jobs. And all these commands are available on all the Cloudy Cluster instances that are launched in the cloud. So the other project that I'm going to briefly touch on is CCQ Hub. And so CCQ Hub is an open source HPC job routing framework. So it runs locally or it can run locally on your laptop, or it can be deployed by system administrator for a larger organization. It is basically it's a unified job submission interface for both local and cloud resources. So one of the goals is to be able to submit your job and have a couple of constraints that say, I want to run this job on this resource if it costs this much money. Or if it's going to take me 3 hours in the queue over here, I should go to another resource and run that instead. So can dynamically route jobs to different resources based on either job directives or certain factors like pricing. And so kind of the architecture on the right is you have this CCQ hub that can run on local resources on a local laptop, so that the big cloud, you can kind of think of the big cloud as either like a campus-wide infrastructure or just your local laptop. And so you can, from one interface, you can submit to all the different clouds and everything, and it plugs in with CCQ and Cloudy Cluster. So if you have a cluster running, you can automatically send your job up to the cloud and it'll dynamically provision it and tear it down just like it would if you were using it normally. And it also will plug into local schedulers so that you can also run on just local resources as well. And also work on data staging, because in order to run your jobs, you have to have your data. So the current status of this is it's all set. There's a setup script that'll run on the local machine and kind of set up a server. It uses PAM for authentication locally, HTTPS and SSL certificates for security, and it currently can route jobs to Cloudy Cluster and CCQ on AWS. We're currently working on the Google addition to this, but it wasn't finished in time for this presentation. So what our next objectives are to be able to route that to the Google Cloud via specific arguments, and the local job-based submission is also one of the next big things that's being finished up. Also the policy routing engine, how do you decide where these jobs go, and returning all the output that goes with these jobs. So just kind of an interesting couple things for ideas. Right now, CCQ Hub can submit to AWS and batch schedulers, but maybe it'd be cool to have it submit to a machine learning service or some other type of one of the other managed services by one of the clouds, or do serverless job execution, or you can also utilize CCQ to just automate a workflow pipeline. Maybe you have some big workflow that you use all the time, and maybe you can automate that via the cloud. And you can also do like I mentioned with those placeholder jobs, you can dynamically construct these quote unquote learning environments where you kind of can mess around and test and do stuff like that. So being able to deploy those with a single job and have all that set up is another idea. And also just integration with local schedulers or other cool software, scientific software that maybe isn't a traditional HPC scheduler application. And I think that's all that I have. So.
So I'm just curious, what kinds of features does it have for error reporting? For example, if I submit really dumb code and I would like to find out about it sooner rather than later, is there any tool for that, or is it on us?
So generally what will happen is the HPC scheduler will tell you that the code didn't run or tell you why it didn't run. There's nothing built into the meta scheduler itself that will look at the code and say that this didn't work. or this isn't going to work. Typically, we leave that to the HPC scheduler, which will spit you back an error file and tell you, this is what happened with your code. This is why it didn't work, or it won't tell you why it didn't work, but it'll tell you this is the error. So you do get all that output. You get that feedback just like you would from a traditional scheduler, but there's nothing that says, it doesn't analyze the code or look at the code in any way. Mm-hmm.
Does the JavaScript syntax support data transfer directives?
So not currently, that is on the list. But at the moment we haven't, that's one of the next things to tackle, is a data movement, obviously. So you can write into your script, data movement, but there's no directives that say move this file or move that file at this implementation. That is something we're working on.
Can one specify a container image to run, like a Docker or Singularity?
You can, but it's not. It would launch. It would be like Docker running on an instance right now. It's not going to spin up a specific Docker container. It won't spin up it's not integrated with the EKS service or the other Google container services. That's also been another thing that we were going to look at. But it would run local. It would run the container locally if you told it to do that, because Docker is there.
And Singularity.
And Singularity, yes. So, okay. Well, thank you.
Thank you.
Oh, who's after me? So.
So thank you for inviting me here. I know this team very well. It's really exceptional set of people the Cloudy Cluster group is. They've done awesome job in bringing resource harnessing and things of that kind, right? So try it out. It's not very difficult, trust me. But so what I'll talk about a little bit about where do we go from here, right? So what are the other things we are doing in HPC? If I manage to put this in, all right? Awesome. So for me, I always look at HPC as a tool. Tool to do something, right? And that something has to work out, right? So I'll talk a little bit about what are we doing. Is it connected or not yet?
You had it a second ago.
Yeah, it fell down. Dang it, Brandon.
I broke it.
Disconnected, right?
Yeah, it was when you pushed me off. It all worked just fine.
Yeah, I want it.
Try going to
So you plugged it into the HDMI and it's currently set on.
Yeah.
You didn't move it?
No, I didn't. It was just connected. Just connected and then.
Plug it in without the little.
It might be the.
Yeah, it might be the second.
Except for you don't have to explain the HDMI.
Just connected.
the way it always
Oh, the
is.
market.
It's always the simple stuff.
It is.
Oh, come on.
I'm here to describe, I'm here to describe the model that cure cancer for the world.
Yeah, and did you
I can
notice
get
that?
this monitor board,
If I had the right dongle to convert it
There
to
we
your
go.
voice.
or worse yet, if I could only print.
That's my first name on there.
We have had it like six, that's
People that go there?
Yeah.
Okay.
Oh, seriously?
So,
good.
so I consider HPC is more of a tool, right? But tool to do something, right? And so some of the examples I'll show what we're doing with it. So I'll talk about some of the stuff we did with the in scientific computing world, and how you can use the same tools which you're learning here for what we call machine learning, right? So some examples I'll give it. So Brandon talked about how you're using a given instance, right? But these instances, as you know, Amazon has these instances are fired up in a given data center, right? So AWS has roughly about 18 plus 1 region. So when you create an instance, you create an instance in a given region. And with that region, as you can see, there are these numbers I mentioned, right? These are availability zones. So in a given availability zone, create a region. So the way we look at compute actually is in 3 ways, right? So what we look at in EC2 instances, you call it instance, or you call it run a batch on it. But we also look at that also as a container service. So for example, compute we look at as a set of containers. Somebody asked, can you run containers on it? So what does that mean? Containers are basically created, it was a mechanism to have what we call resource isolation. So here is an example. You have a CPU, right? You have a laptop. You're using a laptop with one CPU. Can I use your network? So I can schedule a job such that I use your network. You're using CPU because I cannot use your CPU. You're running it, right? So that means if I have to do that, which means I have to isolate myself from you. Otherwise, I'll interfere with you. So which means we'll communicate via something called kernel. So that's how the container came into the business, because now you can have resource isolation by a mechanism called containers. So we look at computing also in the form of containers. The third part we look at is what we call lambdas, right? Or we call trigger-based. For example, your boss gave you a job to do, right? And said, finish it today. So that triggered you to do something. That's called lambdas, or basically serverless computing. So there was no server in the beginning, but suddenly something triggered, created a cloud formation or something, and you got your job done. So that's how we look at the computing, basically 3 phases. One is which does on a batch mode or something like on a large scale. So Cloud Cluster does extremely well, for example, in orchestration of that. So, but you can also look at computing at different scale, right? So some scale, sometimes batches are very good to do something at a second level or hours level, right? So within compute also, there are 3 kinds we have. There are multiple kinds. For example, you have general purpose, but you also have compute optimized clusters, right? So like Brandon showed, that you should use C5 or M4, right? So each compute has a given optimization. So here is compute optimized, for example, for instance, these are general purposes. So you also have storage optimized compute. But there are 2 other kind of computes which are also equally useful, and I think you can do that using Cloud Cluster. Is what we call accelerated computing, right? So you can use it using GPUs or FPGAs. So you already know CPUs, right? So CPUs are basically roughly about 10 to 100 processing cores, but they have predefined instruction set, right? But if you in the GPUs, they have roughly about thousands of processing cores with a predefined instruction set, but they are very highly effective for parallel executions. So sometimes you can use CPUs, but also GPUs are equally valuable. But in some of the workflows you will see is that FPGAs are good. For example, they have millions of programmable logical cells. But one problem with FPGA is that they don't have a predefined instruction set or data path. So that you have to define yourself. So I'll quickly mention that. And there's always an advantage of that, right? So people use these things for a variety of reasons. For example, you use GPUs for deep learning or high performance computing. Sometimes financial computing. There is a talk we are trying to give in reInvent. We are trying to detect fraud detection system using accelerated computing, right? So every day you have tons of people do what we call bidding in the trade market, right? How do you identify millions of patents and say which one is a fraud? So for those things, you need something faster, right? So those are what we call GPUs, or sometimes we use FPGAs for fraud detection system. But we also, sometimes you want to do graphical rendering. So for example, you're using AutoCAD, right? And you're designing a car in a virtual system, and you want to collaborate with 200 people. So AutoCAD uses a type of instance called G3, where you can actually start collaborating for a large set of people. So it really depends on the kind you're doing. So high performance computing, as I said, is useful, but useful in a context, right? So the context here can be fluid dynamics, the example you gave, right? Can be useful for financial or data analytics, right? Can also be useful for weather simulation and also computational chemistry. But it also is useful for things like natural language processing. Natural language processing is a branch of artificial intelligence which deals with how humans interact using voices or mainly vocal knowledge, but also writing part too. How do you do image and video recognition? How do we do recommendation system or autonomous driving? So you can use HPCs for all sorts of things. Another important point is actually what we call the networking, right? So when we say HPC, people say, well, you have to have a low latency. What does that mean, right? It basically means that suppose that you have a system, you're going to GPU 0, right? For example, you run a code on a GPU 0, you're loading some of the data at either disk or the instance type. And if you do that, you go from that GPU to PCI switch to a given CPU. So you always need a CPU for processing. But you can also speed it up by using what we call NVLink. So you can communicate from GPUs to GPUs to accelerate the data transfers, right? So some of the configuration would be extremely useful if you start using some of these links. Security is very important. When you do HPC, you have to make sure that what are the compliance you have. Some people have what we call FedRAMP compliance or ITAR. People say, cloud is not secure or this is not secure. That's meaningless. Well, security has to be with the context, right? What is the context? So it is secure with respect to, let's say, ISO global standard. So security is defined based on what are the compliances you want to achieve. And that's what we try to provide, almost all secure compliance, and we provide a mechanism for that, for the person to use it. So let's look at some of the studies we did. For example, I came from CERN. It has it's the Large Hadron Collider. It has roughly over 6,000 people work there, and it produces roughly over 25 gigabytes of data. This is me in front of a detector called CMS detector. This is the size of a human, okay? And it collides particle at 25 nanoseconds. So with that, it produces roughly about 10 petabytes of information per second. So how do you analyze 10 petabytes of information per second, right? It's huge, isn't it? So to analyze it, we decouple it into two parts. So first we define to do it something which can handle that, right? And go to a second level, right? So to do the analysis at a given second levels, and then you divide into a batch or a given scheduler such that you analyze from second to that schedule, right? So essentially you define from nanoseconds to millisecond using something. And that something is what we call FPGAs. So I showed you in the previous slides that FPGA can do millions. They have millions, of course, can do much faster processing. So you can do that with FPGAs, so you reduce the rate up to millisecond, and from millisecond onwards, you use some kind of traditional batch. So, and that's what we did here. For example, we created an elastic system using a formula. Formula was part of the lab, where you elastically expand your system when you have much more data flow comes in, right? And you created a factor of 5 formula using this mechanism. And this is exactly the same as what Brandon and others are talking about. How do you burst to using a given HPC cluster, right? So this is Brandon already showed. In one of the time, we also tried to study natural language processing. Brandon was one of the key person doing that, and these folks were studying that. And you can see they created over 2 to 3 hours, roughly 1.1 million cores using one data center from Amazon. That's one of the biggest cluster produced for this particular study, right? So what it tells is basically you can yourself create it, and elasticity is vital. So this is basically elastically expanding your cluster from 1 or 0 node to million core. So in any mechanism, I think elasticity is vital, right? So you need these tools. So I talked a little bit about FPGAs. So FPGAs data can be at a given bit. You can define data at any given level, right? Any instructional level. So we have F1 instance in AWS, and here is one study. They try to do high performance data analytics. They try to do it using, let's say, AWS C4 instances, right? The standard CPUs. And they took 3 hours. And when they tried to do using FPGAs, they got it in 3 minutes. So you can do in 3 minutes the things which will take 3 hours. So the way we do FPGAs, I hope you will integrate it soon. We do it in 3 ways, right? So either you do using hardware development kits. That's one of the way to communicate to FPGAs. But also you can communicate using custom OpenCL. So OpenCL, people use it to also do machine learning, but that does conversion to HDR. But also you can use predefined armies. So for example, this is a predefined FPGA army. So you define your code exactly like the way you do, and then FPGAs can compile it and load it in their firmware. I'll skip that one. Those armies you can get it from the marketplace, okay? And this is one of the studies. So people thought to do genomic sequencing will take years and lots of money, okay? So in order to do a given genomic sequence, think about running for 1 year with tons of CPUs. But these guys, they run it on FPGAs or F1 instances within 3 hours for 1,000 diverse patriotic genomes, and they got a Guinness Book of World Record. That's the fastest analytics ever done on sequencing, right? So sometimes having a large cluster is not always useful. Sometimes using a kind of a research type is also super helpful. Much time have. So I'll give you a couple of examples. What else can you do using these kind of framework, right? So for example, let me give you an example of machine learning. So machine learning, lots of people will tell a lot of things, right? If you talk to 10 people, they will talk about machine learning. Everyone has its own definition. The way I look at machine learning, it's actually an intersection of 3 things: supervised, unsupervised, and reinforcement learning. What does that mean? Supervised learning, most of the analytics people do is what we call supervised learning, because you have boundary conditions, and within that you're doing it. Unsupervised learning is somewhere where you define a part of a cluster and how you're addressing a given cluster. So here is an example. When you were young and go to class, right? You want to watch a movie. So you don't know which movies to watch. How do you learn which movies to watch? So you ask your good friend, he tells movie A. Not so good friend, he tells movie B. Which one will you watch? Movie A. So basically, a clusterizing of interest of 2 people in the same way, and then you can predict that person movie A you will watch. The third part is what we call reinforcement learning. it's here, this is an award-based system where you get reward for doing something. So machine learning is, so the way I classify it is that machine learning is used to process complex sensory inputs. So if you have tons of sensory inputs out there, you process it using machine learning. And reinforcement learning is is used such that you can select complex actions, right? So for example, you detect using machine learning that there is a tiger, action is run away, right? So we use machine learning in many things. For example, to detect diabetes. So this is automatic grading of retinopathy. So you train it on a normal eye, and any deviation in this nerve vessels, you can say the person has diabetes, which affected the eyes. So you can do that for image processing. You can also do that for skin cancer detection at much better level. How many people watch C-SPAN? Not many. So most people don't watch it, right? So it runs something on Amazon Recognition. That's a convolutional neural net-based system which automatically detects if a person of this kind of interest, right? And then it sends to all, using as a simple notification service to all the people in order to notify them such that they can take action, like CNN said, breaking news. So this particular framework runs, and so it runs in a streaming mode, right? And does an auto detection system. So you can do multiple things with machine learning, detect object, detect facial recognition, celebrity, many of the items you can do. The same thing you can also do with the voice-based system. I talked about images. Can we do with the voices? You can, and Alexa uses it. So Alexa uses it the way is such that I call Boston, MA. Alexa understands it, and you can say Boston, Massachusetts. She will understand because there is internally something happens what we call speech feature with speaker features. So there's a convolution there, right? So I'll skip this one. It is being used, for example, Ohio Health, where you train it on a given set of patients, but they behave differently in a different settings. At home, a patient behave differently than in front of the hospital. So if there is erratic behavior, because of this convolution happens, they can take different actions, right? So basically, it's a vast array of fields. It starts from image to speech to natural language to also to autonomous driving. And it's really expanding at a much larger scale. But underneath all of that, there is a strong set of HPC to train the models, to use the system, and use it in a much wider variety. So here is one example of autonomous driving, that you can detect the car exactly the same way in the daytime as you can do that in the night. So convolutional neural net has been extremely powerful in doing these kind of things. So with that, thank you so much. Any questions?
Are those white things supposed to be like labeling the types of topics, or what are those white labels in the
Boxes?
Yeah.
Boxes? They're detecting each individual car at a given speed. So it's following that particular element.
But I mean, like what do they say?
Yeah, so they generally, since we actually do some, we're actually looking at the features and that define something, and that box is usually defining the interesting features. That's not telling you what's being detected. That's just kind of a bounding box for the interesting features that are moving, if you're using computer vision models or things like that.
Okay. So define an area of region, right? And that region is in motion or in rest, doesn't matter, right? So you can follow that based on a feature. And the feature is this guy looks like a car, right? Anything else? Any other questions?
Thank you, CJ. Thank you so much. One interesting thing that Brandon mentioned would be an interesting project is taking CCQ Hub and actually turning normal job scripts into something and feeding recognition or those other things and controlling other types of interfaces and stuff. So it's just an interesting thing. I think we'll take like a 10-minute break. People can grab some food, stand up, and then we'll come back and we'll have Vass join us and tell us a little bit about Globus and data movement. Okay, if I leave this here. It was too close. I was looking at his belly.
So there's this cluster gene assembler tried to run queries on web services before, like somebody spun up and provision manually into a cluster. I can't, I'm not sure what.
You are. Nice to meet you.
All right, nice to meet you.
Can't plug into it.
Type for
Software
something.
legs are trying.
Nice to meet you.
Yeah, I think it's really unfortunate. So there's some.
Yeah, you know,
There's some.
Yeah. So one of these CC results is his job.
Exactly. Now without, you know, they come in with all these reports, like we said last night.
Yeah.
What are you gonna do? Right.
And how big they go.
I feel like I don't know where to go to not in some way. There's a shuttle from the hotel. Yeah.
That also, you get more application. That's the other thing. Is that
Obviously, there's a shuttle, you go out of the hotel and then left there into completion and wait for the corner of BAY commerce. All right, well, good luck.
So this particular.
Obviously, are you gonna
Wants to submit its own.
Yeah, no, you're fine.
Yeah, we should disable that functionality.
We'll see it.
All right, guys.
Take your time.
Tomorrow.
Okay, we'll send you some. I'll be at your.
Yeah,
We're
we'll figure it out ways to.
gonna be there like.
So the goal is to find a non-toxic.
You'll be there at that time? Okay, we'll be there. Thank you so much.
And show that that can be false. Hochberg guesses that it is false, so it's, however, no one's found such a graph. Mathematically ruled out all the graphs. They filled out all the graphs. These are the
Oh, so we go you. Okay, so then two of y'all.
And managing the basic.
Yes.
There's a Hamilton.
And also, guys, when this second go, I want to.
You were.
So Hamilton is.
Either way.
When you're going out of the start of not saying more, I don't know, you go to the bathroom. If you were close to the conference, if there was something, then like you
So you take the cycle that has.
recently that we want to see how this tells. Anyway, so we would like to. So that we don't know who is who, but they can still send
That's right.
That basically gives you codes.
Let's go.
Where?
I gotta work it.
You are selling something? It is. Did you see this poster? There's like a little map that shows it. So if you go around the corner here, there's a little map. It's just basically.
How you sanitary with the idea, but now, it's neat that you were trying to get other people to do your research from, before you hear about that, and that, it's a good idea. It's like Project Boiler, except you benefit instead of you giving them.
Can I put that where you talk about airport?
So first into the cloud is really what CCP cloud is. Right now, you can kind of take similar JavaScript and run on the CCP cloud is that interface that we really want to use to
So you get
run on as a jog router and then route to and cloud. What we did is we took the Metaspace or CCQ and we open sourced it and kind of turned it into that jog router. It's on GitHub and
So
that's kind of
basically give it
where we're headed.
data first.
I got distracted with the Google port for body cluster. Now we're gonna get back and CCQ.
And like, presumably, so the client you have the time to see as a stack back.
CCQ hub is open source, so it's
Like average
it's free.
sentiment or.
Cloud cluster is
Yeah.
5% on top of the on-demand instance charges. So it's just
So
whatever you pay for, trying to scrape marketplace and Google.
but I'm thinking they might not have clear labels on all these sites, right? Which ones are from Apple's, right? Comments are from Apple.
Brands on what services.
Yeah.
So and that's what we have that because we actually spin up the lotus and so you can turn that on. They just didn't do it.
What's the joke?
It's not part of the flow of the process, but you can use.
What? And this is, that would be a lot. I know.
You know, chain a couple of jobs. Or,
So they did sit at the happy hour here.
it seems to be a place to know.
Specifically, I understand. So, huh?
I really want to stage the data before you launch. the-
That's cool, because, that's 3 hours.
Yeah.
Why is it silly?
You get your results back.
Those are 3 hours you
Trash
could be
that.
programming.
Well,
Yeah.
or either academic is-
Yeah, I'm gonna do both.
Waiver on egress, so.
That doesn't understand. He also.
I need to go talk to your camera.
Just the applicant. What? Not for you, just like think it's bad. It's just bad. Oh, yeah. If I didn't know any better. I would say you're not.
I mean, right, the kind of where CCQ hub works, you can have the hello world all the way through to, so you can put job hints in and some of the intelligence isn't there, it's really just based on job hints right now. You know, around to the cloud.
What do you have to do?
So the way CCQ handles just. Oh, for Arch. Yeah, Arch, they won't let us put 5% on spot instances, that's what, so it's still that 5% of on demand on top of it. And I think they haven't listened to us. We've asked for a long time. It really just looked like a flat 5%, whatever. They have.
Alright, so. Actually, some of the people out, I'll tell it. So, first of all, I've got a little more. So first of all, I'm gonna tell you all a really funny story. So, you know how, Amy has said that I'm supposed to be in charge of social media? I did something hilarious. So y'all probably noticed I've been going in, changing the logos, make sure everything's good, setting all the information, make sure everything's right on the Twitter account. And then I set the date for today because today's the day of the event. So why not? Balloons came up from the bottom and said, happy birthday, and immediately switched over and said, account locked because you're under 13. So, I'm working on it. I have tickets in to get that taken care of.
Oh, yes, I have.
But having said that, I think there's a couple of you all that already have projects picked out. And there are a couple of you all that are looking for a group. So I want you to go ahead and have this in your mind. Those of you that already have projects picked out, I want you to think of let's do a 1 minute, 60 seconds sounds good. A 60-second pitch for your project. Yes,
Can we pitch ideas that are not the project we're doing? Because we
Yeah.
have all kinds of fun ideas.
that's fine.
There we go.
So you're gonna have a 60-second pitch during lunch. During lunch, those of you that don't have projects or haven't picked your group yet, you're gonna be listening to those pitches and decide what group you wanna go with. Sound good? So, like I said, those of you that have ideas or you're getting ideas from seeing the presentations, just jot them down real quick. You have a 60-second pitch, and then we'll go ahead and pick the groups so that after lunch you all can start working. That sound good? All right, I just want to put it in your mind ahead of time as opposed to later. All right, everything else okay? Is it time?
Bass is gonna speak and then,
Oh, no, I'm not right.
oh, you know,
I'm
yeah.
standing here, but I'm better to do this, so I'm good.
Another small announcement, we have hotel food over there, but we have warm cans of different soda and bars and things back here. It's kind of a contraband area. The hotel's not supposed to do it. You have to find some ice, but help yourself to those. There's more that'll make its way down, so they're all stashed up in my room, so feel free.
Does anybody have any issues logging onto the Slack account yet? Any problems? All right, so guys, make sure you get onto the Slack account. I'm gonna try to grab the emails from Amy and send them directly to you. But also the Slack account's right here.
And they have to decide if they want to use GCP or AWS.
Oh, that's the other thing.
That's a
So
big decision.
GCP, so the Google Cloud Services or Amazon Web Services. So have you already set up Amazon or Google accounts yet? Google? Everybody's Google? I asked everybody else, so that's why I have to specify. All right, so do you want to go Google or do you want to go Amazon? Google, definitely Google? All right, so Google.
Google will set up their lab accounts.
Yes, ma'am.
Perfect, all right. I set somebody up already with a lab account.
Okay, so do we need to give them any information for the Google accounts or?
Yeah, and I'll email it to them as soon as we get the teams and stuff, yeah.
Sound good? Globus guy.
Yeah, I am pretty scary. My dog doesn't think so much.
Yeah. It's nice, but.
I'm waiting for that special email from Twitter. It's like an idiot. There you go.
No, I think
Oh, yeah, they have to.
I mean, I would totally do that.
I know, I'm with you. That's what's bad.
Yeah.
And then I always show my friends, look at this guy.
Look at this guy, no one read our like contract agreements or whatever.
Okay.
They don't have. Actually, no, no one does. Find another proof that all these things are doing things.
Right, right.
So that's the false software. So, the people that make it through are more confused afterwards than before.
Yes, sir. It's a little crap.
I'm like,
Plus R/monitor. That's the thing, right?
Oh, you see people are apparently the only.
Well, I know
ones that
one
don't
thing you can
know.
use,
Because usually goes to LAC's MacBooks.
Those guys have monitors? Yeah, that's
So you see some other things.
You do, you use some ThinkPads. and-
Yeah. Battle stations. Yep, it's a thing.
So now that'll be letting people.
Yeah.
Well, I guess there are a couple of Linux people.
Yeah, that's it. But I guess we're going to start
Does it bother you
Yeah, take it. You bored? I'm gonna stand down so I can type it.
By the way, Ted, I had to go to lunch.
Oh, okay.
You know, so.
The internet.
The one I have in my room. Mine is bigger, and it is higher quality. It's better. The propaganda book.
There we go.
We'll be here for.
Yeah.
We have to see if there's any stragglers.
Like now they're, it's still not filed. It's actually meant by. Yeah, it's Jesus.
I don't know what that is. Your voice.
I said, yeah, that's what I tried to say.
Oh, okay. I was like, no, I delivered. I'm not. Oh, cute.
So I have it signed.
Yes, absolutely. Absolutely, we can switch that. I'll switch that. Yeah.
Okay. Vass is gonna tell us, we've got questions about data movement, and Vass is gonna solve this.
Okay, thanks, Boyd. Good morning, everyone. I'm Vass Vasiliadis from the University of Chicago, the Globus project. And I'm going to take you through a very high speed, very high level flyover of what Globus is and how you guys might use it from the perspective of developers who want to take advantage of some of the services that we built in Globus. Just quick show of hands, who here knows Globus, other than Nathan, who's the expert in the back and can answer all your questions once I'm gone. Okay, so I'm going to do like a 5-minute overview, just sort of from the perspective of an end user and what's possible with Globus. So basically, Globus is a software as a service for managing data throughout the research lifecycle. The core functions are the ability to move data quickly, reliably, securely between essentially any type of system. We have the ability to share data with people from outside of your organization. So it's an easy way for collaborators and colleagues to get access to data that lives on your own storage systems without having to push it out to the cloud or do like weird things with temporary accounts and all sorts of other stuff. Globus uses a lot of your existing identity providers. So if you're with any one of 500 plus academic institutions or nonprofit research groups, you should be able to just log in and use the service with your existing credentials, or you can create Globus accounts to get on there. I like to say that Globus sort of bridges data and people. And what I mean by that is we provide, to first order, a unified interface across all sorts of different storage systems. As you can see here, going all the way from a laptop or desktop machine up to supercomputers of national facilities, instruments, cloud resources, and so on. So we provide a nice consistent view of where your data are and some very handy tools for moving it around and sharing it with other people. Skip that one. One thing you will end up using if you want to access Globus services is this thing called Globus Connect. That's our, if you will, our client software that you install on the storage system, and that makes it available through the Globus service. And I'm going to show you how you do that in just a second. This is a very high-level architecture picture. So what Globus does is at its core, it's a managed file transfer service. So you can initiate a transfer between two endpoints, as we call them. Those are storage systems that have this Globus Connect client running on it. And a user can come along and initiate a transfer, and then data flow between those endpoints. And Globus provides this reliability layer that tracks the transfer and makes sure it works through any transient faults and so on. And if it needs user intervention, it will prompt the user for credentials and what have you. At no time does the data go through Globus, and we don't provide any storage or any of that. So it's really using Globus on your existing storage resources, be they on-prem storage or cloud-based. And when you share data through Globus, what we call a shared collection, what happens is you, as someone who has access to data on the storage system, can delegate some level of access to other people just via their Globus account. So you provide essentially a set of overlaid permissions that dictate who can get to that data. It doesn't touch the underlying storage system, so all the local system permissions are preserved, but users can come along and access that data on your behalf just through Globus. So they don't need temporary local accounts on that system. It doesn't need to be staged in some other cloud service or anything like that. It's just direct access on that storage system. This is some of the types of systems that we support right now. So we have what we call connectors to these systems on the left here. There's a bunch on the right that are under development. I heard you guys might be switching between GCP and AWS. So S3, we've had support for a long time. So if you want to do that, that's there. Google Cloud is still in the works. But I do have a pretty beefy endpoint set up that you guys can use for the duration of this. So let me actually switch over here and just do a quick demo. Okay, so the website is globus.org. And as I mentioned, you can typically log in with any one of about 500 different identity providers. So we've got a whole set here, as you can see. If you don't see your institution listed, you can click over to Globus ID. That's just the Globus username and password. So if you need to sign up for one, you can just go here and create a username and password. But otherwise, you can log in with your Google account down here, Orchid if you have that. So I'm just going to go ahead and log in with my University of Chicago credentials. What this does is it basically redirects out to our identity system at UChicago. I'll log in there, so this way passwords and credentials are not flowing through the Globus service. We don't want to see your credentials at all if possible. We've got two-factor set up here, so I'm getting my notification on my phone here to confirm the login. So once I do that, I get dropped into the Globus file manager. So collections are essentially sets of data on storage systems that you can access through Globus. And you can search. We've got literally tens of thousands of endpoints that are available through the Globus service. So you can search and find one. I'm going to go to my, actually, let me see if I can find, I'll just go to this petrol endpoint. That's a good one. Yeah, petrol Kesbe. Okay, so this is an endpoint that lives on a big storage system out at Argonne National Lab. And I've actually made available this hack HPC directory for you guys. I'll show you the links just a little bit here. So let's say I wanted to move some data to this endpoint so that I could compute on it or visualize it or what have you. I'm going to go out to NCAR, which is National Center for Atmospheric Research. So they have a big archive of, I think it's tens of petabytes of climate and atmospheric data. So let's say I wanted to pull a data set from there and move it to this petrol system. Oops. Okay, so I'm going to move it. I'll just move it into my directory. So this is, I think it's about a petabyte of data. So I'm just going to select it and just move it. So the simplest thing to do is just select the data, click, and off you go. And we'll get a confirmation. Oops. Start. And we'll get a confirmation here that Globus has this request, and now it's going to go off and work on it. And if you want to check it sort of moving along, you can go and look at the activity log. If it's running into problems, this progress bar will turn orange, and you can go look at the event log and see what's going on. I'm just going to let that run. It should take a few minutes, just a terabyte of data, so it's not that much. So quick view into how easily you can share data. So I'm going to go to, actually I can use the system here. So let's say I wanted to share data with one of you or some group of you here, and you didn't have access to this system. Oops, I'm sorry, I'm looking at the wrong system here. Let's switch over. Okay, so let's say I wanted to share this data directory with you. I can go here to permissions, share, and I can create a shared endpoint, as we call it, a shared collection. So I can put in your email, or if it's a group of you that I've set up beforehand, I can select the group and share with you. So I'm just going to say share the data folder with everybody in my microscopy core, whatever group that is. And you'll see here by default that everyone in that group will get read access to this data. I can grant them write access, but if I just do that, then they're added and they have access. So what that means is anybody who can log into Globus and is a member of that microscopy core group will be able to just go and connect to that endpoint and pull that data to somewhere else where they can do something meaningful with it. So just a couple of clicks, they don't need to apply for special accounts, special access or anything. And when they're accessing that data, they're accessing it as me on my behalf. So when you look at that endpoint, what's logged there says, hey, VAS accessed this data. But then you look at the Globus logs and you can see that it was user XYZ through VAS. And we track, by the way, all that detail is pretty fine-grained logging that we have, both on the endpoint and in the Globus service, so you can see who did what. So that's just a quick flyover. And by the way, you can create groups to share with, just the normal group management system. You can create groups and subgroups of policies and so on. Okay, so our transfer is moving along. We'll go check on that later. So that was just a quick view into the web interface, and I should update this picture. By the way, that's our new web app. Nathan's probably the only person, maybe a few of you that have seen Globus before. We literally just launched that app about a week ago. And so if you have feedback on that, we'd love to hear from you. But the other way that and probably more likely you guys will access Globus is through either the command line interface or directly through the Globus REST API. So there's essentially a set of backend services on what we call the Globus platform that expose a set of APIs, and the web app that you just saw is just one client that's consuming those APIs. So the command line interface is another such client. So I can go, and the command line interface is just a set of Python scripts. So you install it, install the dependencies, and then you just run Globus, and it will prompt you with help commands. So first thing I would typically do is do a Globus login. You'll see here it actually pops me out to Globus, log in, and I'll log in with my Globus ID in this case. So I've got multiple identities, and Globus actually allows me to link those identities so that whomever shares with me through different identities or gives me access to various systems, I can get them all through this single point. So here the Globus CLI is asking for my consent for the Globus service to access it on my behalf. So once I do that, I'm here, and now I can do things like Globus, where are we? Task status. Oops. I just forget. Commands task show. It's the old task. So I can go and find the task that I'm running. Let's actually switch over to. That terabyte of data just finished moving, by the way. So you can see it's pretty quick. This was the transfer. So we got, what's that, 4.5 gigabytes. So about 30 some gigabits per second. This is a pretty fast link between these two systems. It's got 40 gig pipes, so the data is actually crunching along there. But anything I can do through this web interface, I can actually look at through the CLI. So I can look for that task, and it'll give me status and it'll tell me that it succeeded, and this is how much data was moved somewhere. Right, so 1.16 terabytes, bytes per second, etc. Right, so that's kind of the command line interface in a nutshell. You can use this to just run commands interactively like I've just done here, or obviously you can script against it. It's just like any other command line tool, like AWS command line tools and so on. So I mentioned that, so underneath all this is this Globus platform. So it's really a set of services for building your own database web apps, right? Be they portals, science gateways, any type of web app, even mobile or command line clients. This is just a very high level view of the APIs. Underlying everything is the service called Globus Auth that does all the identity and access management. And then there's a set of services for data management. The core service is the transfer service, which also has the search capabilities built into it. Actually, that's not a separate API. And then there's other things. There's a search API that's separate from that. The sharing API is built into transfer. And the search API and then identifiers API. I'll talk to those. Those are actually fairly new, and there's some restrictions on use there, but I'm just making you aware of them. So an example of the kinds of things you can build. So we built a very simple data portal. This is a Flask-based web app. You can actually access it, get the details at this URL here, globus.docs MRDP. There's also a version of it running that you can just go and log into and check it out. So it's at mrdp.globus.org. You notice when I do that, it actually has me already logged in. This is part of this Globus Auth, this identity and access management system doing its thing. It does single sign-on, so it recognizes that I already have an active Globus credential in this browser. So it drops me into this app. And here's just a different user interface on another storage system. So here I'm browsing some climate data. I can select this data and then initiate a transfer to some other endpoint. And this will drop me back into Globus to actually select the target endpoint, right? So I might want to put this back on my petrol test bed. Oops, where is it? Right, so exact same thing happening here, right? Here's the data I moved earlier. I can just do submit, and it's just another application that's going against and consuming the Globus API. Okay. What's also interesting in this app, and by the way, this code is all available on our GitHub repo. I'll give you pointers in just a second, so you can actually go and poke around and see how this was done. It's actually pretty trivial code. There's this little service that we added onto it, a graphing service. So this illustrates how you can actually use Globus Auth to have two services talking to each other. So I'm actually here selecting some data, and I'll select a year, and then when I click generate graphs, this is actually gonna call, this application is now gonna call an external service that's gonna go off and generate a bunch of graphs for this data. And it's doing all that. Service is again also an API that's protected through Globus Auth. So it generates my graphs, and then it drops me back into another endpoint where these graphs live, and I can go and click on them, and it's just like a normal browser link, so it's going to pop up the chart, right? So so that illustrates actually a couple of different modes of access. So the first thing I showed you with the data transfer, that was sort of an asynchronous thing where I created a transfer task and it went from the one endpoint at encoder petrol. That uses the GridFTP protocol, so it's an async transfer protocol for moving sort of big data sets. This access mode here is just straight up HTTPS. So I'm in the browser, you can see I'm clicking on a link. It's just normal browser behavior. So Globus has these two modalities for accessing data. They're both sort of secured through Globus Auth. So you've got fine-grained access control sitting on top of that. So you can use either depending on the application. Typically for these interactive apps where you're not looking at huge data, you're going to be going through HTTPS. If you want to move a big chunk of data all at once, you're going to probably use the GridFTP mode. So that's just an example of an app you can build. So this is, I was just talking about Globus Auth. So this is the identity management service. So really our goal here is to make it easy for you to provide login to any app, and you can take advantage of all these federated identity providers that we've got in the system. And you can also use it to protect your own REST APIs. So the same credentials, the same mechanism that you use to access a Globus endpoint or to access some other application, you can have others use those against your own API. And you don't have to build a whole identity system, right? So nobody needs yet another identity. Just use existing ones through the Globus mode. And all of this stuff is standard OAuth and OpenID Connect. So if you're familiar with the OAuth 2 standard, this should be fairly familiar to you. It also means you can access it through standard OAuth libraries, including the Google client libraries, which a lot of people use. And we also have our own Python SDK that uses that. So what you actually saw me doing there, we didn't see it explicitly, but it's a classic OAuth 2 flow, right? From that web app, it went out to Globus Auth. It got me authenticated. I was already authenticated. So actually this third step was done sort of transparently. It got a validation of my identity from UChicago. It gave the app back an authorization code. It then went back with that auth code and got a bunch of access tokens to access the Globus service, to access the graph service, right? And then it turned around and used those tokens to call those services on my behalf. So this is, again, standard OAuth 2 stuff, but this is how it plays out in the Globus context. Probably the most interesting thing you might want to use is the Globus Transfer API. So this is the core service for moving and sharing data. It's a secured API, again, uses Globus Auth, standard URL endpoints for all the resources, JSON documents passed back and forth, right? And you access it with OAuth 2 tokens. If you use the Python SDK, essentially these are the two commands once you have a token, right? So you import the transfer client, and then you just instantiate a transfer client and use that to make the calls. The transfer client allows you to do high-level calls like endpoint search. So you saw me type in commands there to find an endpoint. That essentially you can do through an API call, get a bunch of results back, filter them, get endpoint IDs. You can also do straight up, get some posts and updates on those resources as well through the transfer client. I'm going to show you, I know I've got about 30 seconds left, but a good place to start is at this URL, jupyter.demo.globus.org. So that is, we've got a Jupyter Hub that's set up with a bunch of notebooks. So if you're not familiar with Jupyter Notebooks, it's just basically an interactive Python environment, or any number of languages supported. So you can log in. Again, you'll log in with the Globus identity. Again, it's using Globus Auth. And what happens is when you go into the hub is actually pulling Globus credentials into your notebook, so into the Jupyter Hub, so you can actually access them through your notebook. So you've got Globus Jupyter Notebooks. Globus World Tour is where you want to go. And then if I go into one of these, like platform introduction, this is actually a notebook that has a whole bunch of sample code for accessing the Globus transfer service and Globus transfer and sharing primarily. So I can go through here and just execute these blocks, and you'll see as I'm running through here, right, it gets tokens, right? So all this here is where the authentication happens, and get the tokens. And once I have my tokens, I can just walk through and call methods, right? So here I can get an endpoint, get some endpoint information, right? So there's a JSON document that's returned by the API. So play around with that, and you'll get hopefully a pretty good feel for what the API can do. Let me skip through this. This is a good place for you to start. docs.globus.org/API. That's the API reference. It has links to the SDK, and then a lot of the sample code, including this research data portal that I showed you, are at github.com/Globus. I've put a URL at the bottom of the board there. It's the same URL that's on the bottom of the slide. There's access to this endpoint, as I mentioned. If you want to use it to move data, all you need to do is go and join the tutorial users group. So log into Globus, go join tutorial users, and then you'll have access to this endpoint. Then you can experiment with the Jupyter notebooks, and then hopefully pull some of this into your own applications, into whatever you guys hack, and use it to move data and share data. So that's all I got. Sorry, I ran a couple minutes over, but I'm happy to take any questions. Okay. By the way, that material usually takes about 2.5 hours to cover properly, so if you're all stunned, it's understandable.
So you were saying
Yeah.
there was some space set up for them to utilize?
Yeah, so that endpoint, if you go into Globus, yeah, it's worth repeating that. So this petrol test bed is a pretty high speed, well provisioned endpoint in Oregon. So, and that's the endpoint ID, by the way. So if you're going to access it programmatically, that's what you need. You see the same IDs up here, and you just go into this hack HPC directory, and you should be able to dump stuff in there. If you don't, just
Is
text
that what
me.
you wrote on the board?
That web page is it just has a summary of all this stuff. So,
So then we need those credentials that you had up there, right?
yeah, you don't actually need. I mean, your the actual credentials to access that endpoint are just normal Globus credentials. Once you log in, once you have a Globus credential and you're a member of that tutorial users group, that's the key part. Then you should be able to get to that. Oh, sorry, what am I doing here? Right, so that's just the web page that summarizes it, and I've got links down here to our GitHub repo, that sample code for that app I showed you, the API reference, and so on. But just make sure that you join the tutorial users group. There's a link here. Oops, sorry, right there. Okay, it'll drop you into the tutorial users group. If you're not a member, it'll have a little join button, and you can join. You can join that group, and you'll get access. Okay. All right. Thanks, guys. Have fun.
So next we have, or I can't remember,
No, you don't.
one of the interesting things that we work on is Orange FS in our group, and we actually have Martin and David. What's that? Hey, Mo. And so you're gonna go first and then David?
Yes,
Okay.
that's why I'm coming up here.
No, I thought you were teleporting. Sorry, John. And what Martin does is he works, many years ago, and actually Amy's not in here, she started talking with several.
Some of this is in here, but.
Oh, then I will not say anything more. There's Martin, he's gonna talk. I'll fill in any gaps later.
It's right near the beginning, the history, so if I leave something out, just come back, just interrupt me.
Okay, I'm good at that, okay.
So we're gonna do it. Okay, so I work on the OrangeFS kernel module, which is, well, we'll get into that. Like overview. I assume that most everyone here knows what Linux is. It is an operating system consisting of a kernel and the GNU user space. Does anyone want more, or are we all familiar with Linux? Pretty sure. OrangeFS is a file system that is what's called a parallel file system, parallel virtual file system. And basically what it is you have multiple file system servers which store your metadata and data. And your clients, or when they save a file, the file is stranded across each of these data servers. And the goal of this is to work faster. I wish I had a chart. PBFS, which is what it was first called, was developed in the early 1990s for variable clusters, and which are just supercomputers. And then it was kind of redesigned based on lessons from the original PBFS. It's PBFS2, which was then renamed OrangeFS. They're all related. We've just gone through a lot of names over the years. However, applications had to interface OrangeFS specifically. We had an interface for MPI, we have Romeo. We have several interfaces, but applications at one point were not able to actually just interface it through the kernel. So we developed the kernel module. And this works like any other kernel file system. You mount it and then it shows up in the BFS as any file system on Linux does. And now an application can just use it. This is great, except that we were not upstream. And what that means is that we were not actually built into Linux. We did not come with Linux. We did not, we were not maintained with Linux. We were not, we did not benefit from code changes that were made in Linux. They didn't, we didn't get anything from that. And even worse, when they changed Linux, we were unable to, we actually would not compile and we would have to modify our code to work with Linux. And we were often behind on that, and we would often be in situations where we don't work with the latest Linux kernel until we're able to update it. Frankly, it was a mess. So we decided to go upstream, which means we were going to take our code and submit it for Linux that is distributed by kernel.org. However, they have code standards, best practices they want us to use. And we had a lot of work to do to do that. The upstream development process is rather well defined. It is not as haphazard as some would lead you to believe. Basically, about every 2 months, there is what's called a merge window, and that is when everybody sends their changes to Linus Torvalds. That's the only time you can send changes, new features, bug fixes, anything needs to be sent during the merge window. And there's the RC release candidate period, which goes on for like 8 weeks, longer, 4 times longer than the merge window. And that's when all the testing is done. That's when we make sure that these new features, the two patches don't have problems with each other, that the kernel is actually stable. And at the end of the RC period, a release is made and the merge window opens. The kernel community is very willing to accept new features as long as they are actually used by people, which makes sense. And in fact, they have a lot of features that are not used by a large group of people, but somebody somewhere is using them and somebody somewhere is maintaining them, so they're able to stay in the kernel. This was good news for us. However, they do have code quality standards, and our original kernel module simply did not meet them, and would not have been accepted as it was. So a kernel developer, Christoph Hellwig, he, Hellwig, German, and Mike Marshall, who at the time was at Clemson, but now works at Omnibond, works together to reorganize, and I say reorganize, but that really doesn't do their work justice. They significantly overhauled this code. As it says, they deleted more than half of the code without even removing any features, which you can imagine means there was a lot of work that had to be done to figure out what can be deleted. And obviously what remains is actually in use, and even that had to be significantly improved. And that's just getting it to the point where we can submit it for upstream. That took about a year, I believe. Maybe longer. Then we actually made a submission upstream. That means we actually sent it to the public mailing list and said, this is what we have, this is OrangeFS. We would like it to be in the kernel. And Alviro, who is the maintainer of the VFS, the virtual file system, the whole glue code in Linux that handles file systems, reviewed our file systems. He has to review all the new file systems. And he identified a number of problems with it, but they weren't major problems. They were all minor problems that we were able to make further changes to. One example is that some code that we had that interfaces with our user space client library, which I have to admit you guys probably don't know what is. I did not explain that, but basically we have the kernel module and then the actual RGFS user. We have the kernel module and we have servers running on another machine. The kernel module communicates with a client that runs in user space, which actually communicates with the server and runs our client library. That code was actually changed and is now much more stable. Anyway, once we got all these changes done with Al's okay, Linus Torvalds was willing to merge our RGFS into the kernel, and I believe that was Linux 4.6. And Linux RGFS was part of Linux. At least we got that done. We were officially upstream. And since then, it's actually gone really great because the VFS interface, the glue code in Linux that handles the file systems, is constantly being worked on, constantly being improved. We're constantly finding that new features have been added, that new application level interfaces have been added. And since we are in the upstream code, whenever somebody says, okay, I'm thinking we need to change this interface or improve this either to user space or between the file system modules and VFS, we are considered in that work, and they will actually go read our code and say, okay, well, RGFS needs it to work like this, NFS needs this, ext4 needs this, and we'll be considered in that work. Whereas before we were upstream, these changes just came through and it was done and we had to deal with it. And now we have, not only are we considered, we have a say, we monitor the mailing lists. If something doesn't make sense for us or something needs to be further developed for RGFS to be compatible with it, we're able to voice that concern. And in a lot of cases, these VFS interface changes either improve the situation for us or give us ideas for developing our code further. As an example, for a long, long time, RGFS has been capable of selectively giving you attributes. So you do a stat on a file, a get attr, and you don't want all the attributes. RGFS, you can say, I want M time, I want size, I don't care about the others. And just recently, the kernel has developed a feature called StatX, like stat, but extended StatX, which is the same feature. So RGFS is actually already has that feature in it, and we're able to immediately go in and work that through and make that feature work for RGFS. In addition, many people constantly go through the kernel looking for bugs. Nowadays, that's often with data analyzers, fancier lints really. But there are still people who simply read the code and notice something that they don't think is right. And we sometimes receive bug fixes from the above processes. Fortunately, these are never major problems. These are always minor problems. You have to do a whole sequence of events, and then maybe it might have a problem. But still, it's nice to know that there aren't any edge cases, that we have solved all those. And even better, this applies to in development code. So when we develop code and we send this patch out for review, this is our code that we're going to submit soon, these static analyzers will actually monitor the mailing list and run their analysis on our in development code. And if we've made some silly mistake, we often find out immediately that, I mean, a problem like you do a malloc and you don't check it can fail. You obviously don't want anything like that, and static analysis will find that easily, and it's good that we're able to benefit from that. Now turning to look at something else, recently I have been developing support for the page cache into ArmchaFS. Obviously, the page cache is a kernel feature that has been around forever, basic operating systems. And what it does is an application level read and write does not have to be the same as what is done with the disk. And with ArmchaFS, it's not really a disk, it's a network system, but it's just like disk. The application has to receive the right results. The application has to be able to be sure that data is actually written to stable storage as defined by POSIX. But otherwise, we can cache in memory, and obviously with a network file system, you have the opportunity for another server to make a change, and you have to deal with that. But you can't just cache indefinitely. But an extreme example, we have a kernel test that writes a 16 megabyte file with a 4-byte block size. And if you do each write as a 4-byte write, this is extremely slow. You do the same test with a large block size, and this is very fast. It's kind of the point of ArmchaFS. With page cache, the disk to the server I/O can use a large block size, even though the application doesn't. And the end result is that the application does not have to be changed, and it's often not possible to change applications because they're already compiled. You don't have the source code. You don't. It's a large application. You don't have the time to change it, and the application doesn't have to be changed, and we can still run fast. And I hope this chart is easy to see, but I figure it's kind of small. This blue line here is the result in terms of operations per second and block size for 4 kilobytes, 1 megabyte. This blue line is ext4, the local disk file system. So around 4096, we hit a plateau at I can't do that here, but about 200, a little less than 200 operations per second. And coincidentally, 4096 is the page size on 64-bit Intel machine. Now, with our old code, we followed this red line here, and you can see that the performance went up as the block size went up, but it was very slow in low block sizes compared down here to up here with the disk file system. Now with the page cache, we follow this green line, and we are actually a little bit better than the disk file system for a while. We're a little bit worse, but we mostly follow the same line. These other lines are multiples. We compare single server file systems, which isn't really the point of ArmchaFS, but good for testing with multiple server systems. And you have 2 servers, your performance goes up almost twice as much.
But the small I/O stays efficient.
Yes, small I/O. The point is that even if you're doing small I/O 1024, you're able to hit over 10 times, about 100 times actually, the performance that you got if you were not using the page cache. This test that I mentioned that does a 4-byte write actually increases performance by thousands of percent because it's kind of a contrived test, but it is good to see that. And that's all I have. Any questions?
And this is just This will probably not be in this merge window, but we're hopeful for the next merge window, so this.
Yeah, this is still in development stuff. This is not actually out there yet.
And there's a way to disable it if you do have some workloads that will do funky things with cache. If you're doing any AI workloads or bioinformatics or things that are just doing lots of, regular IO in their applications, they'll seriously benefit from this. And it's been a long process getting this working.
How would you compare yourself to competitors, like for instance, Luster, BGFS, other parallel file systems?
So if you look at the larger file IO, we were as good, if not better. Where we didn't have the capabilities, really in the small IO, and I think we've surpassed the others with this with page cache. You'll see that our performance is significantly better on the smaller IO range. There's, on Ethernet, I think we perform very well across the board. InfiniBand, we've seen some weird configurations where, anyway, there's some optimization that could happen. We're going to go ahead and jump to Terrell.
Okay.
So thank you, Mark. And then Terrell was joining us. We kind of spent the first part of the morning talking about compute, and now we're, you can see kind of a storage theme because they all kind of pull together. And Terrell's going to tell us about iRods and various other ideas around that. So
And I have lots of stickers. So
stickers are awesome. Great.
This should just work, right? That's how this works.
This should just work.
Famous.
We've got this live stream going, so.
Oh yeah. What's your that?
Fair warning. Just want to make sure it's in view. Good.
Just working.
And for those of you that haven't experienced, we have some people that have really seen a lot of HPC. There's a lot of things here. Please feel free to talk to people. There'll be people stopping in and out, ask questions. Don't be shy. Don't be shy.
Yes.
We're all here to learn, and we encourage talking between teams. This isn't a, no, we can't talk to you. It's very collaborative.
Yeah, I want to know more about this team thing. What are y'all doing? What are we hacking? How do we win?
They have to do their pitches at lunch.
Oh, okay. So it's a secret right now. Okay. All right. So I couldn't have known more about what you're doing because nobody knows what you're doing. All right, fair enough. So I'm going to cram a lot of information in a few minutes. And if your faces melt a little bit, that's okay. It's normal. Ask me about anything that sounds interesting. Because some of you may not find interesting. We'll see. So I work for a university in North Carolina, University of North Carolina, Chapel Hill. We make a piece of software that we give away, it's open source. I work for the consortium, which is itself a fake organization under RENCI, which is the Renaissance Computing Institute, which is one of 60 or 70 research institutes at UNC. Most large universities have, especially Research One universities, have lots of individual institutes that get money from federal government for things where they do science. So we are a infrastructure or kind of supercomputing center at UNC, and the iRods Consortium is one of the projects at RENCI. And of course, we're at North Carolina. We are a membership-driven organization. We are not a company. We don't sell a product. We make a technology and we give it away. And the goal is that people can do science bigger, better, faster, with more consistency. And the goal is to get people to use it. We trick them, and they use it, and it runs all their stuff, and then they don't want it to go away, right? Because it's open source, they want to make sure that the software continues to exist and be good so that their stuff works. So they join the consortium and give us some dollars, and with enough people doing that, then we can pay for our own kind of existence at the university and not cost the university money, right? Beautiful model when it works and enough people show up. It's open source, so we're BSD3. You can download all of it, play with it, poke it, tear it apart, find things. It's a distributed system that runs on lots of different computers. And we like to describe it as data-centric and metadata-driven. What that really means is that we are an abstraction on top of lots of our infrastructure. So if you've got lots of computers and lots of storage and lots of authentication technology that your university uses, or your government or your company or whatever it is, we kind of span all that. So we abstract the storage. We provide a metadata catalog where you can describe where your data is. So if you've got files on lots of different computers, you can describe where they are so you can find them again later. It's very handy. We've got a policy engine where you can write code so you can take action on your data, wherever it is, based on the metadata. It's effectively a virtual file system, but it's really more of a programmatic environment in which you can write code to have your organization's data management policy exist and be tracked over time. Can you get all that? The last part is that because it's open source, it's capable of being federated with other instances of iRods. So if your university or your company is running iRods, and they're running iRods, you've got a namespace here and a namespace there. If I go over and they've shared access with me, I can go over there and do something in their namespace, but all of their policy, all of their corporate rules and regulations and stuff is in power over there, but I logged in through my own home. So you don't have to have a new login and password and that kind of stuff, which is very important for big corporations if they want to work with each other. They have a lot of contractors, subcontractors. They don't have to find a new bucket of money and come to an arrangement and put their data somewhere special and lock it down. Their data is already in a place that's special and locked down. They can just share a secret key or something and somebody can get in and do the work. So it's a really important thing for large collaborative projects and like multi-university projects around the world. We sit there. So the idea is that we are an abstraction over all this stuff. This stuff will continue to change. If you're around more than like 2, 3, 4 years, you're going to buy something new and shiny to put your bits on, right? And then the old slow thing that you bought 3 whole years ago now has to go away. Maybe not 3, maybe more like 10 or 15, right? But depending on what it is, this stuff will continue to change out from below you. And the idea is that you can provide access through an API, very clean, and you separate those concerns, which is important. And there's the 4 things. We can talk a little bit about more of these, but maybe not. This is where we abstract all the different storage. To us, all storage is storage. It could be tape, it could be object, it could be a parallel virtual file system, it could be flash arrays, it could be spinning Rust, right? It could be anything. It doesn't really matter because we've abstracted it, and it's just, again, a series of POSIX style calls to that layer. What that means is that we can project, if you've got 3 replicas on different machines, basically copies of the same file, they present as one logical name, right? So we've got a logical namespace that's spanned across physical disks and physical locations. And what's doing that projection is the fact that we use a database. So it's in a catalog. It is the single source of truth. If you lose the catalog, you've got a problem. You've got lots of data, but you don't know where it is anymore. So don't lose the catalog. It's true of pretty much any virtual file system, right? You've got to have that metadata server somewhere. Because of that, we can also write down metadata about those things, which means that you can annotate it with, obviously, nerdy computer kind of stuff, like change times and sizes and that kind of stuff. But you can, more importantly, annotate it with business level information, like this came from group so-and-so, it's part of the red team, and it's in stage 52 of a 150 stage pipeline of genomic sequencing, mumble, something, right? Like you can annotate the data so that when you have code come along later, you can find out that that result set was part of this science on this day from this group, from this funding stream, from this other university, right? So now you can ask interesting questions about the data, and it self-reports about what's going on. You can put the metadata on the data, but you can also put it on the users, as well as the storage. which means that you can start asking interesting questions about, well, what kind of storage is this? Where is this? What time zone is it in? Is it in Germany? Does it have to go through extra special laws to make sure that the stuff is personally identifiable information is anonymized? And then I think one of the most interesting things is the policy engine. So the first 10 years of work on this project was federally funded, and it was all about data grid. How do we keep files that are bigger than fit on a disk together, right? They have to be on different disks. So that was 10 years of research, scientific funding, DARPA, DOD, DOE. This was a hard problem. People were trying to do simulations of physics experiments and things blowing up, and they couldn't store that data on one disk because the disks weren't big enough, right? We figure it out, it's no longer science, right? They don't give you any more money once you figure it out. So the next 10 years of research was adding this policy engine on top of it, right? We now know how to do that. They don't give any more money for that. So now the model has moved to this consortium that we have, right? They expect the market to decide. So at this point, we're the market. You can write code to take effect on any policy enforcement point in the system. So every time any operation in the system fires, somebody opens a file, somebody logs in. Sometimes a database call is made. Every time a network packet goes over the network. Every single one of those things happens at some point in the code. We've got hooks, dynamic hooks, where you can write arbitrary policy. You can write Python code over here that will get fired. That could do things no more complicated than just write down the fact that I was totally in this function right here, right? So if you've got audit logging, if you've got provenance that you need to write down and keep track of what's going on. Larry was not supposed to be in this directory on Thursdays, alert, you can write that and send an email to somebody, right? So every one of those has a policy enforcement point enforced by the architecture of the system, which is interesting because all this stuff is pluggable. So if someone comes along and writes a new interesting plugin, you get policy enforcement points for everything that the plugin author has written by force. So with this, you can do interesting things like restrict access. You can audit the heck out of everything. You can provide context around something. This is from this particular group, from this particular funding agency or whatever, right? You can add metadata to certain things, or you can just send notifications if it's a post. So the operation has a pre and a post hook for everything. If it's successful, it'll go through. If it stops, that's how you could do restrict access. So if your pre-hook said, are you in this particular group? Do you have, whatever the question is, whatever the logic is, and it says comes out with a no, then the operation would not fire. Turn that on its side. Every one of these actually kind of explodes into the others. So here was I'm putting a file into the system. Here's the operation, but the operation itself has to go authenticate, talk to the database, and then write to the disk. But every one of those themselves have pre and post hooks. So it's a nested morass of depth if you want it to be, or you can look at it and say, this is elegant, right? Depending on how you can feel about it. But you can write code to do all kinds of stuff because every one of these plugins has an API, including, I think most importantly, the last one. The API itself is pluggable. You can change the functionality of the server by writing a plugin, and then you get new policy enforcement points based on whatever you thought was interesting. So this is by far the most powerful piece of all this, but it's kind of hidden deep in the subtlety. We've had interesting people show up and write interesting code that we didn't expect. Architecture supports it because we don't have to know what they're going to do ahead of time. I've been talking for 24 hours, so I apologize for my voice. It's only going to get worse this week. This last piece is about the federation. So again, if your organization has this stuff, and it's very powerful, and this other organization has this stuff, you do not have to coordinate ahead of time to be able to collaborate. And that's a really big deal for large organizations that would otherwise have to find buckets of money, put them together, get the people together, have a meeting. This takes a long time. Like projects are slowed down because of the organizational friction. What that means is that we now provide this basically a service interface into this namespace. And when you federate with other organizations, your service interface can talk to theirs. So if these people know how to do like rat brain science, and these people do like crop stuff, and they do space It's stuff, I don't know. You could you can do interesting science all of a sudden in ways that you couldn't before without any pre-coordination. Because you can actually run queries and do science and do compute across these partners in interesting ways. Big picture, our point is that once you have a policy defined for your organization, that's great, congratulations, welcome, that's hard, you've done it. It's going to continue to change. The needs of your organization, the needs of your data sets are going to morph over time, right? If you're doing science, originally it's on your computer. Now, even if you don't have a policy in the grand scheme, capital P sense, right? That's a policy. I don't really care so much. That's the policy. As soon as you try and collaborate with somebody, say you're using Dropbox for class or something, or if you're in a project working with somebody, you've got to come up with a policy. What's the naming scheme? Who's allowed to touch this? Did you touch it last? Copy, copy two, final, right? You have a policy even if you don't really have a policy, right? Put your initials on the file name, right? So as this stuff becomes more mature and you have to do analysis and share it with people and you publish it, okay, let's say you publish the paper. Now, where's the data that the paper was actually published with? That graph on page 7, where's the data that actually made graph 7? To find questions. Most papers don't publish their data along with their science yet. The NSF is starting to get angry about that, and they're starting to make stronger mandates about data management plans, about this science, right? It's not really science if it's not reproducible. The student cluster competition at SC for the last 2 years has been about reproducibility. They will pick a particular paper from the last year's conference that was great and everybody was, that came along with the data and the methods. And then the student cluster competition is reproduce the results from last year's paper, get the same graphs, do it in a more efficient manner, do it without spending as much electricity, do it like, that's the competition, right? If you can't reproduce it, it doesn't matter. So by having a policy in place, you can actually convey what happened, who did it, what the data is, and you can prove that nobody messed with the data from the source to the result. Oh, nice, that's the way it's supposed to work. It turns out that's not how everybody was doing it, it's a secret. Nice thing is that you can go from private all the way down to sustained. Like if you're running a library, put on your library administration hat. Didn't know you had one. If you put on your library administration hat, you have a role to protect this stuff for 100 years. 200, like you have a different mandate when you're in charge of stuff like that, right? You've got to have a policy in place. You can't just have hope that the other person is going to name it poorly and put final into it, right? It doesn't work. And I have a lot more slides, but I think I'm almost out of time. What time is it? It's 12. Right on time? That's weird. So this can be very complicated, and in the past few years, people have written code and done amazing things and also fallen off the cliff because of the dark corners of subtlety, of interactions, of all this stuff, right? What we have done in the last couple of years is kind of, because we're talking to everyone, and we have this wide membership with different motivations. We've got storage vendors, we've got people who are doing the science, and storage vendors trying to sell them hardware, right? And then we've got people who are technology integrators, kind of boots on the ground that go out and install this stuff and configure it and run it. I don't have a beeper. I don't get paged at night if something goes wrong. That's not my job, right? But we train and support the people who that is their job, and they get paid a lot more than us to make sure the stuff works all the time, right? We write the product, we write the technology, and then they do the productization, right? What we have seen and what we've heard is that people want to not write as much code, because it turns out writing code is hard and messy and there's bugs in it. The more code you write, the more bugs you write. So we're trying to help them not write as much code and instead give them downloadable modules and things that they can install and then just configure, right? Not as many places for the bugs to hide. Or if they do, it's our fault, right? So we now do an automated ingest thing. We've got a storage tiering thing. Each one of these is basically a multi-billion-dollar industry, and we're trying to give them away as fast as possible and make everybody upset. It's not working yet. Not everybody's upset at us yet, but we're forging ahead. Our ingest tool is now fully parallelizable. It's based on Redis and Celery and can slurp a lot of stuff very quickly and get into the catalog. Storage tiering, so very, like you've got fast disk and medium disk and tape in the mountain or whatever. We can now do that at speed with some configuration that duplicates a lot of the functionality of very, very expensive products. So aiming to make everybody angry. It's good. I think that's probably enough for you guys. Are you melted? Any questions? You want a sticker? Yes.
A couple of questions.
Yeah.
One, speaking of making people angry, have you guys, are you guys by any chance trying to make people angry in the electronic medical record business?
Yes. So largely the fields that we have gotten the most traction, we started in physics basically 20 years ago when that was the thing.
Good start.
Yeah. And then the archives showed up, libraries and archives records management people showed up because they had this mandate to be able to track stuff well was important. So NARA and National Archives Records Administration, Library of Congress, all that, they've all been a part of all this. We are running the National Library of France's back end. A lot of EU DAT now runs on iRods. We've got a couple conversations this week about things happening in Australia. So it's all over the world, but largely it was physical sciences community, and then it was kind of archives records management community. Now it's basically the biggest thing is bioinformatics, sequencing, genomics, that kind of stuff, because those sequences are pushing out, hundreds of terabytes a day. The light sheet microscopy is coming. Those things are going to put out 10x the size files daily. You're going to have hundreds of terabytes coming out of these things. So you can't do that with a person. The person's not going to be able to keep up with that stuff. You've got to have a policy in place to organize that. Yes.
Yeah, you were talking about how you could store attributes on files,
yes,
et cetera. Is that implemented strictly within iRods, or does iRods make use of facilities in, say, an underlying file system?
Right. So to make it queryable, we have it in the catalog, the iRods catalog, which is a Postgres or MySQL or Oracle database.
Right.
We have technology that has not been released. It's been tested and works at the bench. We don't have it in CI, so it's not released. That will allow us to do for metadata what we have done for storage. So we can abstract the storage completely. We have not yet been able to abstract the metadata completely, but the technology that was called Query Arrow, it allows us to have any arbitrary data backend for metadata. So if you're doing things that would be most efficiently handled by a graph database, like if you're doing a bunch of permissions and things like that, putting them in a relational database is not efficient. It works, but it might be slow. So you'd rather use a graph database for that. So we have that, and the idea is that the query would be handled by us, farmed out to whatever backend metadata system, and then the results get stitched back together and then presented back to the same API. Okay. So yes, but
so you're trying to work towards parallelizing that so that you have
yes.
scalability and so forth.
That
could be. I mean, our metadata server already has. It's not standard, right? On blocks, it has a database.
Sure.
So we can query those sort of things pretty fast. So you could use that if you wanted. Is that what I heard? Or
we will be able.
Once you get to that point.
Yeah, Query Arrow is itself.
Doing that now.
Yeah, Query Arrow is itself a plugin interface. So we would be able to have a plugin that would speak whatever.
Okay.
Yeah,
cool.
As long as you hit the same 4 or 5 things, right? Come in and go out. And every one of those would then again have a policy enforcement point where you could write down, yeah, we asked it a question and we got an answer, but and so you can make decisions about which one is faster or better. Yeah.
Awesome presentation.
Cool. Thank you.
Thank you.
Yeah. All of our docs, all of our code, we're on GitHub. It's all there. We've got all of our training slides are open, all of our fancy pictures. So yeah, definitely poke at it, find a bug, send us stuff. And I'll be more than willing to talk with you a little bit. I'll probably be here a little bit longer and then gotta head back to be the booth babe.
Love
It's the worst job. It's great. I'll just leave this.
So, do we want to have people grab food? Yeah, so there's food, we could take another quick 5-minute break, grab some food, that way you can eat before you have to do your pitches, 5 or 10, you can't do anything in 5 minutes, like 10 minutes. And then we'll have David and Walt, and then pitches for any of those that fill up for pitches or just pitching ideas to others. So go ahead, grab some food, it's out there.
I think the exhibits measuring stuff.
Let me get my bag of those here.
Oh, yeah. No. No,
Where
your dishes, you could just put them here, if you already have dishes, or you could just put them down below.
We have people in our HPC.
Yeah. Yeah, just push all your dishes down there, and just.
Which one did you go?
And we do have some. You like soda?
That's it.
Yeah.
Oh, out there, I'm going.
Well done, Mark. Well done.
20 minutes?
You got it?
Stock fluctuations. Yeah, for companies. So, we have. I did something like that as one and a half hours, right? It's like about that. You analyze installation rates that come from that company. That's usually the water, there's positive or negative, kind of like. So we haven't.
I don't understand, Mark.
I would say I'm shocked.
They don't know my name. Oh, you don't know his name.
George.
We call her at the office anyway.
No, we just.
If you want to do more.
We pick it up, girls.
There you go.
Do a little sombrero, walk around. Have my tea. Yeah, you'd be good.
Yeah, I go after the workday. We can
At the happy hour?
At the happy hour.
Yes, you can be the greeter.
Yes.
I am a greeter.
Yes.
Yeah.
When you don't show up to work, that's the job you get, right?
That looks like somebody doing it.
And, yes. Everything, yeah, it would be.
Yeah.
It's like one package.
Yeah. Otherwise, there's somebody who wants to get that.
You know what?
We have to sort of create a, we have to give that up.
Sure, yeah, I said that, or. I said that. I get it, right?
So, you can go to the movie? Take them down.
Not for you.
No, you don't.
Maybe for.
Okay, if you've seen the movie, that's hilarious.
Oh, yeah, we're running out of.
It's from.
Martin, tell them.
I really like the movie. That's from Thanks, appreciate it.
Yeah, come sit down. You guys can sit. Or is there no There's right here.
Yes. Give it your fine.
That's the old one, I just kind of left it there, because it might actually make sense if I splice it together.
Yeah.
I agree with the audience.
Okay.
So
Yeah, so don't have your speakers on.
but I didn't want, and I couldn't see the project, do this project, and then I go find it process out. It's kind of those are the so it's just,
Yeah. As long as we have some
yeah, and then it has spacers for each task, kind of like the demo. So you can scroll through and then you go, okay, that's.
Yeah.
Yeah. Yeah, I'm real sorry about that, because I kind of was working on my dad to rewrite it, so I actually understood that one part. There's enough words in the blog post if you read through that. It's a lot more.
Yeah, no, I mean, if it's something to do, it's just some of those words, but even if I was like, yeah, maybe they're not able to say that word.
Right now, it's not good enough.
I know.
Well, actually, if you ask them, I might be able to answer it.
Exactly. The problem is, I can say them now, and then when you get up there, I'm gonna go blank, and I'm not gonna be able to get out of the week, so I'm like, sort of.
You can say,
I'll just say I
just
apologize.
say, apologize for which one.
Yeah.
Even if it was.
That might help us get our data out faster.
Seems like they have several.
I like that, that's fine.
People are enjoying them as an possible. I don't know. That's what's there.
It basically is on the front row, I don't know where it is. I don't remember.
My first day out, by the way.
We look forward to
So before or after that.
Sorry.
Exactly. 2:30.
Or like, let's say that I have a file.
Yeah, you can do it on good. I know there's.
Yes.
Oh, that's nice.
Were you having a panic attack? Yesterday. I was worried about that. Yeah. Exactly. I agree. Yeah.
But.
My original video, social media pages.
Oh my gosh.
Maybe have.
So you guys.
And I didn't want to do it before. So, thanks for all the information. In addition to that, I am an actual. About 1 mile verticals. Slipping out. That's probably what's hurt. I think so. And if you don't see it, the other guys are all like. Okay, we were going to stay on it.
Don't stand up.
Yeah, 2,000.
A normal.
Yeah. Exactly.
It's not hard to. What?
Just like H5AI.
And some of this,
What's your most fun?
brown at first.
So you went for something, that's what you did.
And I like to start like.
I did that all the
So you use the other way around, I go in the kitchen, oh, exactly what I'm there for.
Yeah.
Oh, that's nice.
Yeah, I mean, sorry. I forgot. I use it.
That's what I said, you don't have to worry about that, just.
And one of your parking tickets. All right, put it on my list. So I already put it, so don't worry about it. But just tell me and then we'll bring it to okay, and what, tomorrow when you guys come do the same thing that I like. Okay. Since we pay for it. But yeah, we need that ticket to your car.
It wouldn't make sense.
I just wanted to.
But it would be kind of cool.
Yeah, it's probably cheaper for them to make it pretend they're parking on the right. It's true.
I mean,
I don't have a problem with it.
Sure.
I think that's good. It should-
So you could only. She goes, no, you'll be paying.
Okay, we have two more brief talks. One is focusing on cloud storage optimization. So just kind of give you an idea of in Google and AWS how to get performance out of all the pieces they give you. David's going to talk about that for 10 minutes or so. And then Walt's going to come in and talk about parallel IO. He's the original architect of OrangeFS. And he'll be here, but he's really just gonna focus, give you a little bit of overview and give some hack ideas if you wanted to hack OrangeFS. So last two short things, and then we'll be off to go off and scan it.
So I'm David. As he said, he kind of gave an overview of what I'm talking about. Some of my work recently has had me on the pursuit of getting the maximum performance I can get out of Cloudy Cluster and therefore out of the cloud, either AWS or Google themselves. So along those lines, I kind of want to give y'all just a bit of an overview of what you have to look out for in order to get the necessary, the desired performance out of it. So some of the main broader things to consider is the first two are kind of straightforward, obvious. How much space do you need? Is it more important that you have certain performance characteristics? Are you more worried about the price that you're paying for it? Where is the line on how much each one of those weighs? And then the one that most of the presentation will more focus on is what can you do when you're choosing the storage to actually optimize the performance you're able to get out of it. So when you actually go in to choose your performance or to choose your storage, there are certain things that are going to have an effect on where your max capabilities are. And those are your volume type, the size of your volumes, and how many you have in your instances, your actual instance types, and then the number of virtual CPUs within those instances. So in these next sections, I'm going to have one with GCP, and then we'll go over AWS. And just before I start those, I want to preface it with, there's some specific numbers here, but for the most part, this will be a general overview of what you're looking out for. But it's not going to be the numbers you see. While there are similarities and it looks very similar between the two, they're not a direct comparison of AWS versus GCP. For specifics, when you're looking at things like the throughput and IOPS, the numbers that they broadcast, they use different IO sizes to calculate those. So it's not a direct one-to-one, oh, this one's more, this one's less. You have to look at that and know that there's some different variables there. So more just an overview of in each cloud, this is the way, the things you need to look out for to make sure that you're getting the most you can. And we also assume that in addition to the storage options that you choose, you're choosing an instance type and setting things up so that your network is capable of supporting the bandwidth that you need out of your volumes. So for GCP, there are a few different volume types that you can choose. The lower tier standard persistent disks are your cheaper per gigabyte option. And they're still good performance, but they're lower performance compared to your SSD persistent disks, which are going to be more expensive when you're going per gigabyte. But because of the way that your performance scales, your capabilities, your maximum capabilities scale as you increase in size. If you're needing really large IO intensive performance, it can end up being cheaper because you might not necessarily need to buy as big of a volume to get the same amount of performance or even more performance out of it if you are getting an IO volume or an SSD volume. And then we also, they have local SSD options that you can choose that gives you the most performance. Granted, you pay a lot more for them, but in terms of Cloudy Cluster, that isn't an option that you'll see to choose. So just a brief look at some of the maximum capabilities that there are. In GCP, so we have sustained IOPS, IO operations per second, and sustained throughput. So if you set up everything in the right way, the maximum, for example, read throughput that you can get out of a standard persistent disk is 180 megabytes a second. And the maximum out of an SSD is 1200 megabytes per second. So there's a lot of numbers here, but they might not necessarily mean that much to you right now. The bigger question is, what do you need to do to make sure that if you need this much performance, you can actually get it out of your cluster? And so to actually optimize for that, just to take an example for standard persistent disks, In the standard case, you don't have to worry, as long as you have, as you see, as long as you have more than one, you don't have to worry about how many virtual CPUs are in your instance types. As long as you have two, it isn't going to be a limiting factor in what your maximum performance will be. The only factor that you have to worry about is your actual volume size. And so you can see here that if you want to get that maximum 180 megabyte per second read throughput, you have to have 1.5 terabyte volumes. Anything less than that, it's a linear going from the smallest volume you can get up to 1.5 terabytes. The performance increases linearly with the volume size that you get. So you can, there's charts that I can share with y'all at the end of the thing that will show if I need this performance, I need to use at least this size volume. Going to an SSD persistent disk, you do have to factor in the number of virtual CPUs that you have in your instance, in addition to your volume size. So you can see that in order to get the absolute highest performance out of SSD volumes, you have to have an instance type that has at least 32 virtual CPUs. Anything less than that will be sort of along the same lines. It'll scale linearly, that you can get more and more performance as you get higher and higher virtual CPU counts. But if we go back and look, you can tell that what I was saying earlier about depending on what kind of workload you have, it might not necessarily be cheaper to do the standard, even though it's a cheaper per gigabyte price. If we look, you can see that in order to get 3,000 read IOPS out of standard, you have to have 4 terabyte volumes. But you can see that at only 2 terabyte volumes, you can get 60,000 read IOPS out of SSD volumes. So if that's the kind of performance you need, it can actually come out cheaper per IOP. So that's something that you have to factor into your calculations when you're deciding what kind of storage you want, what's more important to you. So now moving on to AWS, a lot of it is the similar types of things that you need to look for, but just in different ways. So they have a general purpose SSD, which is going to be the default option when you spin up or when you launch an instance from the AWS console. Or if you need higher performance and are willing to pay higher price, you can get provisioned IOPS, which give you a dedicated amount of IOPS that you can achieve from that volume. And there are also hard drive based options that you can choose if that's something you want, that you don't need to pay as much performance, or you have a specific less frequently accessed data, things like that, where you can afford to take the hit there and you get cheaper prices. So along the same lines as when we looked at GCP, you can tell here that the numbers we look at are a little different. We're giving your IOPS per volume and your IOPS per instance, and throughput same way. So what's interesting to know here is that you can see, regardless of whether you choose GP2 or IOPS volumes, your per instance limit is the same. So for example, with IOPS, regardless, you're going to get 80,000 per instance. So where that comes into play is how many volumes you're going to have per instance to actually get there. If you have GP2, for example, you get 10,000 IOPS per volume. So you're going to need at least 8 volumes to achieve the maximum performance that instance can give you. Whereas you can use less volumes if you use the IO option, because each volume itself has a higher capacity. So to actually optimize AWS to reach those goals, similar to GCP, so we saw with GCP, it was determined by, well, when we were looking at the SSD volume, it was determined by how many vCPUs and your volume size. It sort of correlates the same way because it's dependent on instance type, and that instance type gives you a certain set number of vCPUs. So it's still related in the same way, but not as much where I can say I want this instance type and give me 32 vCPUs with it. It's I choose this instance type because I have that many vCPUs and other factors. So if you see it, to actually get the maximum IOPS or throughput, whether it's a C5 18XL or the equivalent highest tier memory optimized instances, there's a long list of the different ones, but pretty much each one you can see, and I can share that chart as well, is the maximum highest performance largest instance of each instance type is what you would have to use to be able to actually reach that 80,000 limit. From there, it scales down with each size instance to lower levels. So if we look here, let's say we were trying to get the maximum per instance throughput of 1750 megabytes a second. We know that a per volume limit is 180 megabytes a second. And also from AWS's guidelines, anything less than 214 gigabytes. There are options that can get you the maximum 160 megabyte per second if you have burst credits available, which I think somebody mentioned a little bit earlier, but that's where essentially you get a limited amount of burst credits. And if you're doing your whatever job you have, if you're not using all those up, it's fine. You have a certain limit, you're not reaching those limits. When you actually get to a point where, okay, we have something really intensive that needs to reach this, it can burst for say 30 minutes up to a higher number. So you can choose a smaller volume size, less than 214 gigabytes, and you can burst to that maximum. But if you choose something over 214, you're guaranteed that regardless of burst credits, you will get that maximum performance. And so here, kind of what I mentioned earlier, if we look between general purpose SSD and provisioned IOPS, you can see that, let's say we were trying to get IOPS, and either one, our maximum per instance limit is 80,000. But if we choose general purpose, it's going to take 8 volumes of at least over 3,000 gigabytes to reach that 80,000 limit. Whereas if you choose provisioned IOPS volumes, you only need 3 volumes and per instance, and they only have to be 640 gigabytes each, and that will guarantee you the 80,000 per instance limit IOPS. So that's basically a very quick, brief overview of some of the things you have to look out for. Obviously, there's much more information and there's much more detailed charts from AWS, from GCP that will tell you exactly if you want this IOPS limit or you want this much throughput guaranteed, you need this volume, you need this instance type. All of those factors come into play. So by far not an exhaustive look, just a little bit of a heads up of things you want to keep an eye out for when you're trying to choose and when you're wanting to make sure you're getting a certain amount of performance. Now granted, with what you're doing today, depending on what your projects are, you might not be trying to get 80,000 IOPS and trying to pay for the largest C5 18XL instances. But going forward, that's just the types of things that you have to look out for and be prepared for to achieve the actual desired and level of performance that your application may need. So that's about it, unless there's any questions or comments. All good? All right.
So we have one more quick session. Do people want to do the pitches right after this talk? Or do you want a little bit of time before you come back and do pitches?
Let's do it.
Do it right after? Okay, great. And you don't have to have if you don't have your idea solidified yet, you don't have to pitch. It's kind of for those that people, you can also just give other people ideas too.
There's like a shelf.
Yeah, that's right.
Cool, thanks, Peter.
I highly doubt that.
Is there anything else besides beauty?
Yeah, like.
No. Can you? Just like.
Even with this. I'm okay with that. You know exactly what I would do. If we want to play.
Basically. Oh, my card, right.
Think about it.
Yeah, we'll like get him to take out.
I'll see if you know what I'm talking about.
Yeah, you. Yeah, like.
Seriously, Peter, that's your brilliant strategy is to, this will be an access group. Have you looked at the scales here, man?
No. That's why we're getting the fourth person to do it.
Oh, okay, I got you. Did you get it? Okay, I'll tell you. Just we'll put this up. Yeah.
We don't have a converter. USB-C.
Oh, no, I'm not talking.
Yeah, VGA.
Someone else.
Yeah, exactly.
I'm with my left hand, that's awesome.
I think yes.
Change that glass? Yeah. Press it. I really don't know what you're talking about. No. Sure, that's all right. What? I said I do When did you become?
Yeah, I bought one that has.
What?
Like $100.
Oh. I don't have a network.
It has network too.
How exactly? Wow.
Yeah, it's good to go.
I don't think that's true. Stop. Don't finish that sentence. No, the rest of this was, but through here.
All right. My name's Walt Ligon, and we've been doing high performance file systems since about '93. That's when our first one was done. In '94, I was at Goddard Space Flight Center working with this guy. He took me down the hall into this guy's office, and there was two of them in there, and they were had these wild eyes and hair that stuck up out all over the place. And they said, "Yeah, we hear you have a file system." And I said, "Yeah." And they said, "Well, can you run it on Linux?" Which was brand new at the time. I said, "I'm sure we could. There's nothing unusual about it." So we're going to do this thing where we're going to build this parallel machine, you know, and kind of describe it. Well, what they were describing was Beowulf. The guy I was meeting with was a guy named Tom Sterling, that you may have seen in one of the plenaries or something like that, or walking around. In any event, that's really where the file system started. And then come 2000, we decided to completely rewrite it because my grad student decided he hated it. And we wanted to completely rewrite it. And it's been like that since. So it's got about 18 years of life on it. This is about the same time that Luster was being written and a lot of other file systems, GFS, IBM GFS, and all this. And we were in a community at that point. We would meet together, all these guys working on these different ideas, and talk about what we were doing and how we were planning to do this, planning to do that. We kind of all shared stuff. It was kind of a very neat time for me. Later, we started getting into this, the cluster people saying that they could do, it got it kind of ugly, but let's not get into that. That's not what I came here for. Came here for was to talk about parallel I/O. So today, almost every high-performance system, large high-performance system, is some form of a parallel computer. It has a large number of nodes and even larger number of CPUs or maybe GPUs, and it takes a single problem and divides it into potentially millions of little pieces, and then works on those in parallel, periodically exchanging data. If it doesn't periodically exchange data, we call it embarrassingly parallel. And that's just what computer science is made up, because if you did this analysis and you ran it on that kind of a program, everybody looked at you like, well, of course it did well on that. That was easy. So it's embarrassing, you see what I'm saying? But that's basically the form of what we do. Parallel computing, the idea was to multiply compute cycles in memory to get faster computation. And for many years, that's primarily what they did. And they really didn't think much about I/O. And it wasn't until the 90s started to come around that people started looking around going, we're not going to be able to do anything useful with these great big parallel machines we've built without an I/O system. What we were doing with them up to then was we were developing algorithms and seeing how fast we could run them, but not worrying about how long it took to get the data in and the data out. Well, then people started realizing that over that time, our technology had scaled to the point where we were running everything at a very high rate of speed. So we need to keep those CPUs and memories busy. We need to keep them doing stuff. If they're not busy, then they're a waste. And the people who paid for the machine get upset if they find out you're wasting a large percentage of their machine. Okay, literally. They can be millions of dollars, and that's what they're about. In the most recent times, the last 5-10 years, this phenomena called big data has come along. This was, well, we're not just worried about computation, but most of what we do involves moving data in and out. The genomics research is a perfect example of that. Okay, I mean, there's got all this data, and you got to move it in and some other in and mush it around and then get the results back out. And if you can't do that fast, it doesn't matter how fast your CPUs are or how many you have, because they're going to slow down to the slowest part of the system, which is getting it in or out. Now, there are lots of ways to do I/O. The one that the vendors, people who sell you hardware, like the most is the one great big server with these big, huge cables and then, lots and lots of disks behind that server. They like that because those are big, giant machines that they sell for a lot of money, and that's what they want to do, is sell you this sort of a thing. But what we were into, and is what I think is becoming more and more, well, it goes up and down in terms of interest, is the parallel approach, where we take small or medium servers, maybe servers just the same size as a compute server, and spread the data across. So if I take one file and I might write parts of that file to 8 or 16 or 10, however many separate servers, okay? The idea being that later I'm going to come along with a program and it's going to have 32 compute nodes going along, 32 processors doing computation. It's going to want that data, and they're all going to go grab it kind of together. We'll be able to spread out and parallelize the I/O subsystems, the memory on those servers, the network. That's a big part of it. When you only have the one server, yeah, okay, they have a big fat pipe, but there's only one message can pass across that pipe at a time, even though it's really, really fast, and you could get collisions. And if we get what we call contention is just a word that means that messages or even computation are trying to use the same resource as another one, and they run into each other. It's like traffic out on the streets of Dallas. If you've been out there, okay, that's contention, and when all that traffic builds up, okay, and even though they build big wide freeways, it can still get all built up and it's not moving very fast, okay. So that's really what we thought was the interesting thing, was to build a system that parallelizes the I/O the same way we parallelize the computation. And we built a file system called PVFS back then, which stood for Parallel Virtual File System. The reason it's called that is the very first version was actually integrated to another product called PVM. PVM was the MPI of the 80s. MPI didn't exist back then. There was something called PVM, Parallel Virtual Machine, done at Oak Ridge. And so we actually integrated the file system into that package. Okay, well, when we did the second version, we made it a separate beast on its own, and that's the one that we have today. Okay, so OrangeFS is the successor to PVFS. Okay, in other words, most of the code from PVFS became OrangeFS. Why did we change the name? Because a lot of the people who worked on it decided to go on in their career and do something else, and we just kind of wanted a nice clean end. And we also at that time decided we wanted to be able to do different things like support cloudy clustered stuff like this. And so we changed that word. It's open source, okay? It's very open source. Anybody can come get it. We don't make you jump through any hoops. You don't have to sign anything or tell us your name or your email address. And you can email us and say, hey, I'm having a trouble, and we will generally jump on it and help you. Now, if you're calling, emailing us 3 times a day, we may slow down a little bit. But for the most part, we're eager to help people do stuff. It's very easy to use. Runs all at the user level, except for Martin's kernel module, which is actually pretty small and even smaller than it used to be. Everything runs at regular user level, which makes it pretty easy to work on, pretty easy to make run well. And we compiled it on lots and lots of different versions. And most people say the biggest thing we got going is it's very easy to use. It's highly configurable. You can set up all sorts of parameters. I'll get to some of those in a minute. This line, I think, is a big part of it. It encourages experimentation. When my grad students designed and wrote this thing, one of the things they thought was, I want other grad students who are wanting to work in this area to come along and use this as a platform. And there are hundreds of people around the world, China, Russia, Europe, and lots of places, South America, who have done just that. They've used OrangeFS as a platform, and then they've added a cache or to do something, whatever it is they decided they wanted to do. Basically, you can take that and redistribute it as long as you keep all the original attributions in it. So that's part of the reason why it should fit this hint thing. We'll see. And it works with a lot of systems. I had to write one more thing. 3 wasn't enough. Now, this is basically the architecture. There's 2 main pieces to this. There's the client, which obviously is where the user code is going to interface, and a server, which is where the data is actually going to be stored. Now, if you look on the client, the big part of it is this thing we call a system interface. And I'll mention that in some later slides. But the system interface basically implements the equivalent of system calls. So they're all named PVFS _sys _getattr, IO for reading and writing, setattr. I'm drawing a blank, but there's 20 of them, something like that. They all sit in this one directory together, and they all use this thing we call a state machine, okay? So a state machine, I didn't put a slide here for state machines, but basically at the top of every one of those files, you see a little block of code that sort of looks like C, but it obviously isn't. And basically what it allows you to do is to set up a group of states, and in each state you can go run some C code. So you could put the name of a function you want to run. And then afterwards you could say, based on the return code of that function, you can go to another state and run his code. And the main reason we do that is that there are lots of times inside of this thing that there's concurrency, potential concurrency. So we've decided to do something that's going to take time, like send something over the network. We don't want to block the server. Okay, now we could use threads. Of course, back when we did this, threads were a little bit squirrely, more squirrely than they are now. So that's what a state would do. A state would say, here we're going to call a thing that's going to block, then we'll let other state machines run. And they interleave, just kind of like an operating system would. And then down below that state stuff, there's the definition of each function that's declared in there. So you can follow the trace through the path up in the state machine very easily, and then you can go down and look at these things. It's a little bit weird, but again, it's done that way to manage the concurrency. We use the exact same thing over the server when we get over there. Then on top of that is, there's the kernel module. That's Martin's kernel module. MPI-IO, if you're using MPI, that code usually will interface directly to our file system. There's also something called a user interface. There's some of the hints, the hints, the hack hints, whatever, are going to reference that. Server over there, for each one of those system calls we have here, we have another state machine over there. So if I, am going to run a get adder, it's going to go across the wire, and it's going to hit a get adder on the other side. It's a little bit tricky the first time you want to modify that list of sys calls. So the things I'm going to show you aren't going to do that. They're going to work primarily in the client or primarily in the server. But I've had dozens of students learn to do it. It's not that big a deal. And there's even a little document file that says, here are all the things you have to change. So anyway, now we get over to the server. Over on the server, everything is an object. The objects, we call them namespaces for whatever reason. And each object has two components. What we call a byte stream, which is just what it sounds like. Sequence of bytes, could be as long as you want. And key value pairs, that's where all the metadata goes. Okay, so in fact, that's the thing I was wondering if we could work with the IROD stuff, because that actually sits in a database and it's pretty fast. So we could put things in there and then he could send requests to sort those things, what have you, or search, what have you. So that's basically what's going on over there in the server. And again, there's a lot to it. Now, this is a diagram that shows you how we implement a file or a directory, okay? Each one of these boxes is an object on some server somewhere. They can all be on different servers. They could all be on the same server. We don't really care. We have code that assigns a new object to a server. We usually use a random approach, just randomly pick one, but you could actually modify that as well. This first object is what we call a directory, and it contains the metadata of the directory. So it contains things like who owns it and the last time it was modified and all of that kind of normal stuff that you would put for a directory. It also has stuff like how many dir datas do you have? Okay, that's the next block over, and some stuff like that. Included in here for each dir data, there will be a reference to a dir data. A dir data is kind of like a chunk of the directory. Instead of having the directory being all in one place, we can break the directory up into chunks and spread it out across 8 separate servers if we want to. This allows us to have multiple tasks trying to look for an item in the directory all at the same time, okay? Directories refer to dir ints. A dir int is one of the things in a directory. So if you have a file that sits in a directory, then that file is a dir int. That's what they call them in Linux as well. Okay, in other words, it's got the file name and it's got points to the metadata and all that sort of stuff. And that's exactly what this one does. This dir int here points to that metadata up there. That's now going to be a file. So this whole thing here is a directory. Not just this, I know that says it, but it's the whole thing. If you look at what you think of as a directory, it's some metadata and a list of stuff that's in the directory. Here's your metadata, there's the list of stuff in your directory. This represents a file and it's the exact same thing. We have a metadata object, and then each of these contain the data of the file, part of the data of the file. So again, that's how we get our parallelism, is we can put those on separate servers and then go out and read them in parallel. Okay, so that's basically how we organize these things. And it's important to kind of get that idea and understand it. Otherwise, you start to wonder what the hell's going on. If you go and look and say, all right, we're going to do a mcdir. You start looking at the mcdir, and it's going to create, this directory, and that's going to create, other things. And you kind of go, what is all that? Well, this diagram kind of shows you. And I actually have a whole presentation that goes into internal structures that is available. I'll put it out there. So that's the basic idea there. All right, let's get past all the stuff that make your eyes want to roll back in your head and talk about some hack ideas. Okay. One of the things that I've always wanted to do, and in fact, when I designed the file system, I built this kind of support in, was to be able to do I/O using MPI data types. Now, if you haven't used MPI, you may not know what data types are, but basically they allow you to describe a region where you're going to either send data from or receive data into. And that region doesn't have to be contiguous. In other words, it can have a chunk and then skip some, another chunk, and all this kind of thing. And it's designed cyclically, so even if it's really huge, it only needs a few pieces to describe a large repeating structure, for example. That's standard MPI. And I thought, MPI people, if they'll know how to do that, they'll want to do this. So we built in to the server the ability to take that information and use it so that the server could read and write that way on the file system, just the same way as MPI. Unfortunately, POSIX, that defines the I/O interface, doesn't have a mechanism for providing this this piece. Okay, so we need to modify the user interface to do this. Well, we have our own implementation of the POSIX interface. It was called the user int. It was back on one of those first slides I pointed to. So I'm gonna get to that. I'm getting to that. Okay, and so all we really have to do is go in there and figure out how to pass in one of these MPI data type structures, and then there's already a place for it in the request. We're already doing one, but it's just the one we're doing is real simple. It's just a contiguous set of bytes. So we replace that with this thing, and now we can pop in one of these structures and go out and read data from different points in the file all simultaneously. That saves you a lot, because if you have to go out and come back and go out and come back and go out and come back, that's very expensive. Okay, what we want to do is have one pass that can do all of this. So we have to modify that user interface. Okay, that's our user interface. It looks like POSIX, but it's not governed by POSIX. Okay, there's something called a PBF request. That's the thing that describes an MPI data type. MPI data type, PBFS request, same thing. I just called it something new, so we knew this is the one for the file system. The PBFS sys.io is the system call, the sysint call that would do this, because it the one does read and write. Okay, and then finally, the user int direct interface is where we would find the implementation for reading and writing data, and we could fix this thing up and do it the way we want. So that one is, this is actually a relatively easy project. A group of people could, I don't know if you can get it done by the end of the conference, but you sure try. I had an undergraduate student one summer played with it, and he didn't quite get it done. But again, I think this is a cool idea. It could really impact performance. Another idea. We have no locking, unlocking whatsoever in our system. Our system is all designed around that, so you don't have to have it. It would be really cool though if we had a read, modify, write operation that operated on a extended attribute. Okay, and extended attributes again were the ones that IROD would probably want to play with. So it's just an attribute, but it's in a different set of them. So what you would be wanting to be able to do is have a numerical value, for example, in there that's 1 or 0, and go out there and check it. And if it's locked, then you just return that it's locked. But if it's not locked, then you lock it and return. It's called test and set. You guys have seen that. It should have been in your operating system class. If not, Google it. I guarantee you'll see it. It's a very simple one. There are much more complicated read, modify, write operations like fetch and add and stuff like this. But test and set is very simple. You can write a piece of code that gives you the description of what it does. And pretty much what you'd be doing is taking the existing get attribute and set attribute codes and sort of modifying them into a new operation. You would not have to modify anything across to the server. So some new system interface stuff. Trove, you might need to look at Trove. That's the back end on the server that actually does read and write. I don't know. You might want to support that over there. And then implement test and set, like I said, is probably the easiest one to do. Performance analysis. This actually lines up very nicely with what Martin and David talked about. It's really very important to be able to have a system where we can go through and sweep parameters. In other words, if this parameter can be from here to there, then let's run multiple runs and be able to check things and say which one of these things gives us the best performance. Okay, so like the number of servers. If I keep increasing servers, does it go faster and faster and faster and faster until it burns a hole in the rug and disappears? Probably not. Probably when you get the number of servers large enough, the overhead of dealing with that is going to cause it to slow down. Okay. So it's important to do that. The number of server processes per server. You can actually run multiple servers on one box. And as far as the system's concerned, it doesn't care. The reason you do that is you can use the networking more efficiently when you do that. What are the size of the user I/O buffers? This is exactly like what Martin was showing, where you had wasn't you, Martin? You had the real small I/Os to the real big I/Os. Same idea, only this is measuring across the network to the servers to see what that does. The time between I/O requests. If you jam your I/O requests together real tight, you're going to really stress the system. If you spread them out a little bit, they may run better. I mean, so can you get a measurement of that? Size of stripes. That's when we have data distributed to multiple files, we call the amount of data that's on each one a stripe. Okay, so it's just a number you could set as a parameter and change things. Different networks, like David was talking about, and kernel parameters, again, like Martin was talking about. But there's others like the number of transfer buffers. Okay. We usually find the defaults work great, but there have been some cases we've measured where they wanted to change this. This is a memory area between the kernel and the user space that we pass data through. So how big are those things? Caches. We've got tons of caches. There certainly is Martin's new cache, but there's also something called the attribute cache and the name cache and the cap cache, and there's just a bunch of them. And usually the thing that controls those is the timeout. In other words, how long can you leave an item in that cache before you, say it's too stale and throw it away. Because if you go too long, then you may get an error because the data has changed and you don't see it. If you go too short, then there's not much point in having the cache. So these are all things you can measure on different systems, different speeds, different number of machines, and you may get different results, okay? And this is the kind of stuff, just like what these guys have done, they've done this and gotten papers out of it. You can start with something like this and get a lot of parameters that may then guide you looking at one of them and going, hey, I wonder if I could modify this and make it do better. And then you get, a paper out of that, so. There is another OFS hack. There's lots and lots of things. I've been doing this for 25 years. There seems to be a never-ending collection of projects and things, dissertations and what have you. So if you're interested in this stuff, we are perfectly willing to try to help you get started using the code. It's pretty efficient. It's very similar to BGFS. In fact, I keep wondering whether they stole our code. It's got some similarities to Lustre. Lustre runs the servers in the kernel, which is faster, yes, but it means every time a new kernel comes out, it's a real pain, and they have not been able to get their code upstream because it's too big, too complicated. So, I mean, we kind of always go back and forth with that. All of these are good pieces of code. Some of them are a little better in one situation, some in another. This is not a bad one for, hacking on, because the ideas in there are going to play over to any other system that you work on. There's a guy named Garth Gibson. I don't know if you know who Garth Gibson is. It's at CMU. He was the guy who wrote the original paper on RAID with his advisor, RAID arrays. And he did Panasys. If you're familiar with Panasys, he was the chief technical officer of Panasys. Good friend. And he was telling me the other day, he said, when my students need to do a project in the file system, hey, we don't use ours, we use yours because it's very, very easy to work in. So there's that. That's everything I had to say. Any questions? Yeah.
Does OrangeFS support snapshots or transparent file system compression?
No. Those would both be interesting projects, although whenever we look at something like that, one of the first things I ask myself is there a layering opportunity? Can I get layering out of a standard, file system that does snapshots and layered on top? And that may work, and it may not. And but yeah, that's a great one. And the compression, no, we've not done the compression. There's probably a good room for that. Yeah.
All right. A little off base, yet kind of on base.
Uh-huh.
So the locking and unlocking is usually due to parallel processes, multiple compute nodes. So having said that, and just your personal opinion, do you think NFS will ever go parallel based upon that? Or figure out a way to go parallel? Since it's the easiest way.
Well, there's PNFS, which they built and kind of worked, and then nobody would pay attention to it. I remember, some of the guys in that group I talked to during that time. I don't know. One of the things that I know to be true I don't know if it's true, but one of the things I believe is that you won't get the efficiency and speed up with a proper POSIX implementation. You have to bend or break POSIX in some spots. We certainly do in some spots, but we don't get a lot of pain out of it, and it's set up to where you can make it not do that with an external locking system. So yeah, there's that. I mean, I'd love to see that. but just having watched that whole thing, because I mean, that project was another one of the ones that started back around 2000. And so, you know, we used to meet once a year in Santa Fe and everybody would talk about all that stuff. That's good. That's a great question, though. Thanks.
Well, thank you. Pitches.
Yeah.
Any volunteers for being the first to throw out ideas?
I'd love to probably tell someone though. Yes, yes.
Here it goes, Jack's going first.
Yeah, Jack.
Just stand in the frame of the live stream.
Everybody get your tomatoes ready.
So I'm Jack, and Ted and Michael are on my team. And so our basic idea for a hack was to ingest lots of review data and see, kind of make like an economic model off of it, see if the ups and downs in review scores match the ups and downs in the stock market prices for companies. So we'll take like, I don't know, Microsoft and find reviews for their products and try to build an economic model and see if there's a relation there.
That's awesome. All right then, good job. Next, are you going next?
Sure.
Good.
So my team isn't set completely on our idea, but we really like machine learning and what's it called? Language modeling?
That's my process.
Yes, that one. I've been thinking about it for like hours, but just escaped my mind. Yeah, so like a novel technique for training a machine translation model would be really cool. But if you have a cool idea yourself, we're open to hearing other cool ideas, maybe an easier one, but you know, something related, anything that's doable. But
So are you going to start from scratch, or you want to pick something to work from there?
By starting from scratch, do you mean in terms of?
I mean, open up a blank file and start typing.
No,
as opposed to going and saying, oh, here's an older model and see if we can build on it.
Yeah, so if I mean, we would use TensorFlow. And
Wait, we're not building our own.
yeah, so I mean, like really specifically, the idea is to rather than just start from take a string, train a model to map it to the string in French, you take advantage of known like word by word translations, so that your model has a lot less to learn, and then you can train from there.
Good job.
Remember, everybody, when you're picking up things like that, all the great scientists stood on the shoulders of giants. You're not, as long as you're not copying, but using the ideas as a starting place. That's good.
Hello, I'm Prashant and my teams are Ryan and Bumnut. So we're not sure about our idea yet, but we're trying to build something like a cloud-based note-taking system where like we get data from the students, like the images of their notes. And after we get data, like we try to analyze like, is there a relation between a good note-taking and GPA and like job success? And then like we'll try to like see if with different universities, different institutions, if there's like a relation between a good note-taking strategy or a study habit and train an AI. so it can predict like how it is related in education.
That's wonderful. Anybody else? Good.
She always do that.
I'm Nathan. My team members, David and maybe Mark, I'm not sure who's helping me out. But I sort of have a plan A and a plan B and maybe some fallback plans depending on the technical feasibility of plan A. But I was hoping to take this sequence assembler called Canoe. And right now on our local cluster, that's currently an application that consumes a lot of the node time on the cluster. And there has been one group of researchers at our institution that have attempted to run that on AWS. They manually spun up a cluster, ran Canoe assembly on it, turned it off after a while, and they ended up spending like $10,000. And so I think with Cloud Cluster, it seems like it should be feasible to do that for cheaper in a more automated manner. Some of the difficulties could be that this application wants to submit its own jobs to a Slurm cluster. And then it uses job dependencies as well. And so I really don't know enough about the technologies involved to know if that's feasible to make that more efficient. And then plan B, if that doesn't work out, it might be, there's this large phylogenetic inference application called RaxML, and I have a sort of a high throughput computing task that my supervisor gave me to get done on that, and it seems like that might be an easier thing to do. I was planning on using Open Science Grid to try that, but yeah, this could certainly be an alternative.
Anybody else? Anyone else want to go up there?
Okay. Okay, so let's make sure what we have here. So here are your choices. Flip this over. All right. So from what I heard, please tell me if I'm wrong. So we have team one that was looking at stock versus what?
Reviews.
Product reviews.
Yep. Reviews. Okay. Team two was.
Natural language processing. Yes, and TensorFlow. Yeah.
Processing versus using TensorFlow. And if I misspelled that, I'm sorry. I use a keyboard. TensorFlow to do what?
Machine translation.
Or machine translation?
I think that's what it is.
So you're saying as a service?
Only if we have extra time.
Okay. All right, group three.
That's note taking strategies versus educational consistency of success.
Job success versus what?
Note taking strategies versus job success.
All right, and then number four was assembly-esque.
Yeah, genome.
Okay. So do assembly basically. Am I doing that right, or did you?
Genome.
Oh, genome. Okay. So we have four choices here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 people. Think to yourselves and think hard. We're going to give you a minute, about a minute. That sound good? I want you to take a minute and decide which one of these projects you need. If you need more information, so project leads, could you raise your hand? These are your ideas, you came up front, that's why I said project lead. So the project lead, yes, that would be you. There we go. So look around as for the project leads. If you have questions, go ask them. Sell your product, gentlemen. You ready? Siri, give me a 1-minute timer. It's holding on. All right, she's ready to go. All right, 1 minute. So if you need to ask and talk, please do.
And find people on your teams if you want, form your teams.
Yes, form your teams.
Why not? It says, wow. Do you think it's fun on the other side of the rainbow? No. We're just gonna dish it out while they're talking. The entire UD. We got a minute now. No.
All right, guys. 1 minute. Siri said 1 minute's up. Y'all ready?
Yeah, might as well.
Okay. So team one, how many people do we have that want to work on team one?
Great.
So we have 3. Okay, team 2? 3? Team 3? Okay, we got 3. Team 4? We got 2.
2. And do you want, who do you want? Oh, you're on the, okay, you're gonna work with him. Okay. And we also have a guy from Berkeley that is gonna work remote with you guys.
Oh, so we have somebody from Berkeley?
Some.
So 1.
He's from Berkeley, he's gonna remotely.
Okay, so we have 1 sub-R. So that means we have even teams. All right, guys, so here's what's gonna happen. You all know your teams. We're going to give you some mentors to help you out. I'm gonna warn you, so I've run a couple hackathons now at this point, and Alex has too. What I suggest, before you jump in, I know y'all have been thinking about this, you're super excited. Remember that you have a limited amount of time. The real goal is to make small blocks, small chunks that you all can handle. That you know that I can get this block done, then we can go on to the next one, and on to the next one. If you try to take the whole thing on as a whole, failure is imminent, I'm just gonna be honest. Take small blocks, small chunks, small things that you think you can accomplish within 1 to 2 hours. It's that bad. And break it out like that. If you just jump in and start coding, you're not gonna get it done, flat out. All right? So having said that, I think we're gonna split them up. Where did Alex go?
Alex
here. Alex, stop feeding your face.
What? I'm busy.
Okay, so
And Jamie, we're gonna split them in rooms too.
yes, that's what I was gonna say. So we're gonna split you all out in different rooms so you all can work together. We're gonna give each of you all a team mentor to help you out, to kind of guide you. But beyond that, before we split, what's the plan for the rest of the day?
It's free, open, I mean, whatever their schedule is, you guys can, I don't know what your time frame is of how long you guys wanna stay here or can't stay here, but We could do till 11 o'clock tonight, and then, tomorrow morning, the room's open at 8 AM as well.
So as far as in tomorrow, do we have any final presentations? Do we have any final, because we're probably not gonna meet like this too many more times.
Yeah, and that's, I think those are targeted for 7, but if everybody votes, we want to push it later. If we have the room later, we can push it later in the evening, so it's really.
So what are your schedules of when you guys would like to be done to present to us tomorrow? What do you think your time frame is that you guys can all have the projects done and present us tomorrow?
I mean, we could set the time early and then push it back, or we could set it later and then have it be at that time.
So, I agree.
Something to add for.
So here's what I'll say. How about this? So let's say, first of all, we're gonna meet back here at, what's it, 6, 5?
No, 4:30
4:30? Okay, so we're gonna meet back here at 4:30.
in this room.
Kind of in this room, we're gonna get a systems check and make sure everybody's good to go. And we're gonna send you back out. Tonight at, our scheduled time to end tonight is 8:30, right?
No, they could stay till 11.
True, but I'm just saying our scheduled
Oh.
time is 8:30. So let's meet back in here at 8 o'clock. So we're gonna have 2 meetings. We're gonna have one at 4:30, then we're gonna have one at 8 to kind of check and make sure where we are. It also kind of allows your brain to step away for a second. You'd be surprised how much that helps. And we'll see where we are. Tomorrow, we'll get started, but we will have a group check-in at, let's say, 10 o'clock.
Okay.
All right? And then we'll aim for us being done right now tentatively, let's say 4 o'clock. We'll do presentations at 4 o'clock. How's that sound? So let me put this on the board.
Oh, you put it on the board?
Good.
I'll put it up here. So we have
You can also send it through Slack.
4:30.
4:30.
And you guys will have your mentors with you and all, they will be here in and out as well. So honestly, ask them questions, don't sit there and be stuck. You wanna take your progress and you wanna move it forward as fast as you
I
can.
like this color. Okay, so.
I agree. Thank you.
The room, we gotta get that one. We have 3 rooms.
Oh, we need to use ours?
Yeah.
Okay, so first, now, let's do that. Okay, and all. There's a little bit too,
So it was just, I mean.
I'm good. Peter?
Yep, that's fine.
We're heading out to SC18. I think it was here. Cool.
All right, so let's get y'all into some rooms. I'm gonna go get that together while you all chat and start to get your plan together. So remember, 1 to 2 hour blocks, guys, 1 to 2 hour blocks.
They don't have work.
Yes, we have two teams stay here, or they can stay up there, we'll show you.
So I need 2 teams. 1 team stays here. I'm gonna suggest the guy that's carrying the monitor to stay here.
And all the other teams, we could break you guys out.
So, team 2?
2, 3, and 4.
2, 3, and 4. That's right. That's 4 teams. 2, 3, and 4. We have the rooms for.
And then the table outside. Okay. Wait, we'll do that. Let's do that. I don't know.
You guys have, I was gonna suggest my half.
I chose my words carefully.
So I think that they do.
Okay, so here, let me write this down. Right? All right. So that's the thing, that's what we need to focus on.
Okay, so, but, hold
You
on.
guys have fun.
Thank you. Thank you.
So,
Yeah. All right.
Oh,
Do you want to put it on paper instead?
I'm sure. Are you?
Hey, I'll do this, or you can do that. Pick one. No, pick
None of
you
that.
make a decision. Good.
Alright, so, Michael, you're very decisive, but you make everyone else do the decisiveness for you. You're just decisive that you wanna have it done, and then you tell them.
No, because I have no preference. If I had a preference, then I would make a
Alright.
decision. Usually, I force you to make a decision instead of waffling backward and forward.
I wonder why that might be.
Okay.
Alright, so we need to get data.
Do you agree that that's the primary, should be the primary goal, just getting data?
Yeah, I kind of hope that we can, I know that that's the primary goal of what we're doing, but like, I kind of hope we can do a little bit of analytics on it, because that's the fun part, is doing the
Yeah, for
analytics.
sure, yeah.
But yeah, I understand what you mean, because once we've got the data, like, our avenues to play with it are, there's a lot of avenues we can use to do that.
Yeah.
So given everything I think we've seen so far, I think the best idea would be to get all of our data ingested into an S3 bucket in some way.
Yeah.
And then we can use any of the services, like these, that cloud thing, or we can use our EMR stuff. There's a bunch of different things we can do to run stuff on once we've got it in an S3 bucket.
That makes sense, yeah.
Okay.
What about data format? I don't know what S3 bucket is.
So S3 is Amazon's simplified storage system. Basically, the way that it works is that you can store things, and then to retrieve them, you have like a key, and that it's like a giant hash map.
Okay.
Except it's like files.
So it's a file system.
It's basically
Yeah,
just
kind
a
of. That's what I know
round
about it.
trip.
I don't know too much about it.
Clearing out one of the other rooms so you can actually see outside.
Whoa.
If you want.
Awesome.
So you're not stuck in here. We're just
We
gonna
are,
do all
we
this
are a
stuff.
little cooped up,
Yeah, this is kind of like, anyway,
Let me pack up.
then you get a key for the other room.
Oh, yeah.
That's cool.
I mean, that case is a 5 case.
That does look kind of cool. I don't know what it is.
Alright, so we need to format data, we need to run some kind of.
Yeah, so for data formatting, I think, well, first, I think we should have two separate main files. The first one being the aggregated data for the stock market, and the second being the aggregated data for reviews. Or we can split up reviews by company, so that you get like a bunch of
I think he's here.
reviews at a bunch of different times.
Yeah.
But that should be the two basic divisions between stock market data and.
Well, there's,
Oh, and interview data.
how many teams do we have?
I'm thinking the stock market data will be. Yeah, so I think the hard.
Guys, I can't count. You guys can stay here, or if you want some light.
There you go.
Is it too dark? Well, this is very natural light in here. I've been here for 2 days. Good, kind of. Yeah, sorry. I thought we have 4 rooms and this is one of the 4. I can't count. So, but if you guys, but you can also move down to the lobby if you want at some point. Just kind of go find a corner in the lobby.
If you need a little light.
Yeah. if you need a little light. So, sorry, I can't count.
Okay.
I was trying to look out for you and I didn't do a very good job.
Anyway, so.
Well, I think that room will be available.
So the two big data divisions that we're using
The work week.
using
Oh,
Spraker.
they changed the veto.
Well,
But.
should the
What
us?
I'd like to do is
What
just
one
do
group should
professional reviews of the customer. Yeah, because if the customer reviews are really low, but the professional reviews are very high, and there isn't a bit that might say like, hey, these things are important, right? Yeah, so like, that's an interesting conclusion too. Yeah. Do you wanna write some of this down?
Hold on a second.
Okay.
I'm sorry, I'm thinking.
Alright, back on.
I think we're saying.
Well, yeah, 30 minutes we're leaving, that's what I think. Yeah, so I am gonna back up. Yeah. because we did this. I did tell you where your backpack was before we left. And now you're well aware of it.
My bag.
Or my bag, I had some space, not a lot, but some.
Some space.
So James Shrewsbury, at one point, was trying to get on the stock data, and he failed. And he then started scraping the web server on when he was scraping for stock data.
Yeah.
And then after that, I think he found a higher resolution source. So I'm gonna text him and hopefully.
So like for my Confidence project, I took historical stock data, right?
Yeah.
And it was just like price on closing day. That's all we need, right?
Yeah, but he got higher resolution data, I think.
Oh.
Like he got like minute or hour or something like that.
Okay.
And that's,
Do you want to send
because I know that like,
because the thing is, I just texted him. He'll probably get back to us by the time we get back from
that's
Okay, so that's good.
So like,
obviously the finer
granularity
granularity is.
would give you the.
Well, so another thing we'll do is we'll give us an excuse to use the fact that it's higher than high performance computing.
Sure.
I mean,
Well, all of this gives us an excuse for that.
well, my point is just that like we've got $1,000 of AWS credit. We can do a ton of processing. So we should be trying to pack as much information into this and see as many different as much analysis as we can.
Yeah.
So there is kind of a work area out there, a little table. You could sit there if you want, or you can stay back here, whichever, or you can just go in the lobby, whatever.
We're gonna go on a walk for a bit to the conference to get some fresh air.
Okay,
We'll be
awesome.
back. Thank you.
Okay, awesome, thank you.
We can move it now.
30 minutes.
We need it to, part two.
Yeah, okay, so we need to get data into a three bucket and we each have to make sure that it's formatted somehow so that we can process it. I'm not trying to think really discrete tasks.
Yeah, so the formatting of it won't be difficult. The primary problem is getting the sources. Once we get the sources, it shouldn't be too difficult to format.
I have a list of 10 websites that are straight from.
Okay, so do you have do you know a lot about web scraping?
I have done it before.
I think all three of us have done it before, but no one really likes doing it because it's kind of annoying.
Yeah, I've done it before too, but it's kind of.
I was actually looking through some code the other night from an Android app that did a bunch of those web scraping. So we're running it on Android.
More stuff.
But I can definitely try to repurpose it.
Okay.
I've got code that I use to scrape for all that site, but that wasn't really all that challenging. I was only scraping one data point.
So yeah, I was doing something very similar with that.
I scraped
Something I've done.
tables before, but
Yeah, well, I think
we're probably
our
going to scrape one data point.
yeah, our task is
Did
basically.
they explain to you?
Um,
We have two spaces that you can consider.
Oh, they
They
said
explained,
there was a little.
there's a little lobby out here, but then there's another room that the other group is in. It's a pretty big room. They're in the, on the second floor on the other side where the rooms are.
Okay,
So you get to pick which one you want.
awesome, okay,
If you don't want to stay back here.
okay, thank you.
So,
So scraping.
yeah, so if we do scraping, it's gonna be one data point. The only reason I want to everything is because it's gonna make us have to go to each of these websites and find a way to navigate to each of the product pages.
Your phone is all the way
And
there?
somehow get enough technology there. Then after that, we
Okay,
have to.
I was
use
gonna say, I
the
have a
Your phone is all the way
scraping
there?
for each site. We're
Yes.
not just gonna have like.
How good is your battery? My battery. Oh, you,
So
yeah.
basically, it's setting up.
I'm getting ready to get another one. I'm going back to my iPhone.
No, my iPhone has an
Really
82% battery. It dies.
Real mentors and figure out.
Well, I'm one of the eight.
Did I give you guys your Amazon yet? Your Amazon code?
Yes.
Okay, so you guys are set with $1,000.
Yes.
Okay, so you guys are set with
Jamie,
Okay,
if you
so let us
give
know
up
if you need
the
something.
people at Google,
Oh, so Amy, I think Amy's taking care of that, the
Google.
I just gave them the Google thing. So they have their Amazon account, I gave them the Google, I need to give that other guy the Amazon. And then I gotta go over to the other people right now.
Check out. And the only thing is we have to ask you is, who do you have slated as mentor?
Anyway, so the point is, so I think it would be on
Everybody in a long sleeve shirt.
I think it might be more helpful to try to find a large body reviews.
And I need theirs.
That people can use too. Yeah, well, maybe as a core to start off with, that's something at least like get off the ground.
This, I will be back, ma'am.
So do we
Now
have
we'll
enough time?
I'm trying to get this settled.
Yeah,
Yeah.
that would be really nice.
I'm trying to lead it.
Right. So I think that would be a really good way to start, and then we can do,
Yeah, for sure, that sounds cool.
Yeah, I mean,
There's gotta be some sort of tool where that's a web scraper that puts it in an S3 bucket where you just give it a tag from a web page and it goes and grabs that. You know?
If
Like
there isn't-
an HTML tag, you know?
yeah, I mean, if there isn't, then we ought to be able to make one or something, or I don't know if that's worth our time.
Yeah.
Amazon Cloud data repository.
There's probably stuff in AWS though, yeah?
Hey, look at this.
It's gotta be a hookup for that.
Look at these reviews. Look at these numbers of reviews.
Nice.
Yeah, so what we're looking at is more like, how do you want to do products? What do we want to focus on?
Well,
oh yeah, that's another good thing to consider. What do we want to start focusing on? Because like, we'll want to do this for like one company and then maybe expand it to different things. So what do we want to start with? Do we want to start with an electronics company?
So I think that we actually, we'll get better results if we do something that's relatively less volatile. Because if you're doing a company that's like always releasing products and they're always going up and down, then they're probably gonna swing a lot more. So that might give us more data to work with, but I'd say we want something that's a little bit more medium because.
Okay, so suggest a product.
So
TVs.
Televisions? Okay.
Yeah, TVs are.
Okay, so my problem with.
Electronics that people buy less frequently. That's
So
why-
my problem with that is when we're looking at stock prices, we're not looking at the whole body of everything that's put out. So if like, if you look at Samsung with regards to TVs, we've got phones, laptops, washers, like all this crap that's gonna go into it.
But it's also a diverse set of products and they still do major releases for each product and you can. film what
Another
products are.
thing to think about is that as long as we're using things that are.
We could do cars.
That would be really.
Because the manufacturers
Yeah.
put out only a small selection. They're
A flagship every year, or 3 flagships.
right, so there's got a small product selection. It's gonna be relatively stable because they can't just keep shipping out new cars throughout the year.
Yeah, it's perfect.
The professional reviews on it are gonna be, you know,
meaningful.
yeah, and they actually might be more meaningful than like the user reviews.
Yeah.
So that could be a good.
Well, but
good
user,
case
I
study,
mean,
I
that's an
guess.
interesting thing to consider also is,
Yeah, it's the user reviews too.
And-
The only thing I see difficult with that is gonna be the Amazon review set.
That's
because-
exactly what I was gonna say is,
Yeah.
if only if they sold those on Amazon. I think that the processing though should be pretty similar. Before we throw that away though, I think the processing should be pretty similar. So as long as we do a test data set, as long as we like get stock data on one company and we have all of our software running so that we can like make a graph with one thing, we should be able to then turn around and make the same graph with another stock and other thing.
For sure,
Yeah, that's, but we should start with one thing that we can at least like
Yeah,
get like nicely build out and then build in other companies as we're building it out for this one.
Really, for hackathons, all you need is proof of concept. I've done lots of hackathons where the end result was just a pile of crap, but it looked nice and.
Bad Jack.
And like it had a
Standard.
nice concept in there, like it was like, we could take this, you know, throw it all away and restart it, but like, this is a viable idea, you know?
Yeah, so yeah, I think that the thing for that would be to find a more stable company that we can.
Yeah, I agree.